Hadoop is a set of technologies that's used to store and process huge amounts of data. In this course, I'll focus on using Hadoop to process data rather than setting up and administering it. We'll take a look at business scenarios where Hadoop is an appropriate tool. I'll also cover libraries such as MapReduce 1.0 and MapReduce 2.0. In addition, we'll take a look at Hive and Pig, which are often used in Hadoop implementations. Finally, I'll show you how to tune MapReduce, and I'll give you a sneak peek at some of the other new Hadoop libraries. There are a couple of things that you should know as you get ready to start this course. The first is I expect that you have a bit of a background with relational databases. Some in administration, but more for queries will be helpful as I'll be making comparisons with Hadoop queries to relational database queries. In addition, some of the samples I'll be showing in one or both of these programming languages. I'll be focusing mostly on Java, but some of the samples I'll be showing in Python. And also, if you have a basic familiarity with Linux commands, since my samples will be running on the Linux operating system, that would be helpful. When we're working with Hadoop clusters, we have a number of choices that we can use when we set up those clusters. Basically, there are 3 different ways. We can use the open source Apache Hadoop binaries and set up our Hadoop cluster either on our laptop or on an on-prem set of servers. We could use a commercial distribution, such as that from Cloudera or Hortonworks, which as of this recording has been purchased by Cloudera. Alternatively, we could use a number of configurations on the public cloud. In this course, I'm going to use the public cloud for most of the Hadoop cluster demonstrations, and I have a couple of tips to keep your costs down. For most of the cloud vendors, there is no free tier for managed Hadoop services, so you're going to want to start with a small cluster. You can actually use a single virtual machine if you prefer. However, I like to have a couple of worker nodes, so I usually use a 3-node cluster. On the particular vendor, you want to set up a budget. I usually set up around $50 or $100 and an alert. It's really important when you're done studying that you shut down your cluster. You can incur substantial cloud charges if you don't do this. As you move to production, there are a number of very important vendor optimizations to keep your costs down. From Amazon or AWS, you can use EC2 spot instances. Or for Google Cloud Platform or GCP, you can use Google Compute preemptible instances. And I'll put links in the references to this course so that you can take advantage of these optimizations when you move to production. As we start our journey learning about the Hadoop ecosystem, we're going to look at the landscape of databases as they exist today. And that is using relational databases such as SQL Server or Oracle or MySQL. Now, as more and more data becomes available and companies and organizations want to embark on big data projects, they're running into limits around using relational databases. What are those limits? The first is scalability. Many companies have projects that are in the gigabytes. The new world of big data is moving into the terabytes or even petabytes. And although it is possible to scale traditional relational databases to the multi-terabyte or even single petabyte ranges, it's very complex and very difficult and very expensive. Also, some of these big data projects have different kinds of needs around data ingest or speed. A lot of times my customers will say that they need real time, which again, relational database systems are not necessarily built at the scale and the speed to be successful in bringing all that data in. And there are other considerations around queryability, application of sophisticated processing like machine learning. Relational database technology is not going away. This is a key concept as you're learning about the Hadoop ecosystem. The Hadoop ecosystem is designed to solve a different set of data problems than those of relational databases. Speaking of databases, there are many choices now, more than we've ever had. I've been working in this industry for 15 years, and it's really the most exciting time since the beginning. So these choices do include file systems, surprisingly enough. Now, before the Hadoop ecosystem was broadly available, it was common to find information in file systems, maybe even in XML. And this does play directly into the creation of Hadoop and the ecosystem. because one of the core components of Hadoop is an alternate file system called HDFS, or Hadoop File System. And it really is designed as a replacement for whatever file system that you're currently using. And it's got a level of sophistication around management of data in a file system. So in this course, we'll be examining the HDFS file system in some great detail. In addition to that, along with relational databases, we now have the ability to look at other types of databases. So in the NoSQL world, there are a number of groups of databases, and they can be broadly categorized by the following that is listed on the slide here. Key value stores, such as Redis, column stores, document databases such as MongoDB, or graph databases. And for some big data projects, NoSQL databases are an appropriate solution. It's important to understand that while some implementations of portions of the Hadoop ecosystem could be categorized as NoSQL, Hadoop itself is actually not a database. It is an alternative file system with a processing library. Now, most commonly in Hadoop implementations, you will also have a NoSQL implementation. So, sound complex? Kind of is, but I'm going to guide you through all these complexities in this course. And of course, as I mentioned previously, relational databases are still around. They're not going to go away. They're designed to solve a specific set of data problems that Hadoop is not designed to solve. So really, when you think about bringing Hadoop in as a solution, it's going to be in addition to your existing RDBMS, not as a replacement for it. So Hadoop itself is most commonly implemented with something called HBase, and we're going to be covering this in pretty good detail in this course. Hadoop, as I mentioned, most commonly will use an alternative file system, which is HDFS. Now, this is based on technology that was developed originally at Google to index the entire internet, which was called the GFS, or the Google File System. What Google did about 10 years ago is they wrote a white paper on how they created this file system, and the open source community took the information from this white paper, and it was part of the basis of Hadoop. So if you hear GFS and HDFS, they are very, very similar implementations. HBase is a NoSQL database that is very commonly used with Hadoop solutions. It is a wide column store. And what that means is it's a database that consists of a key and then 1 to n number of values. And let me make an example so you can understand. Let's say you had customer and customer information. In a relational database, that would be 2 separate tables, maybe even 3 or 4 or 5. In HBase, you would have a customer ID, and then you would have the various customer attributes as key value pairs in the wide column, such as name is Lynn and location is Irvine, so on and so forth. What makes a NoSQL database NoSQL is that this wide column implementation can vary. So my next customer might have a name, but might not have a location attribute, because the width of the column varies dependent on the amount of information that's inserted. And that's called a wide column store. To understand more about the use cases for Hadoop ecosystem, we're going to take a look at what's called CAP theory or CAP theorem. And you may have heard about this if you study databases in school, but it's kind of an interesting way to understand the different categories and classifications of databases. So the first aspect of CAP theory is the idea of consistency. And the concept is that there are certain database solutions that allow for very high data consistency. And another way to think about this is that the solution supports transactions. So an example of a transaction would be if you had 2 data modification operations and they were combined as a unit. So withdrawing money, for example, out of a savings account and then adding that money into a checking account. You would want both of those changes to occur successfully or neither. Otherwise, your data would be inconsistent. So certain classes of databases support strong consistency. The second aspect of CAP theory is availability. And another way to say that is uptime. So what this means is that you have the ability to make copies of the data so that if one copy goes down in one location, the data will still be available for some or all of your users. And the third aspect of CAP theory is partitioning. And another way to think about that is scalability. And what that means is that you can split your set of data across multiple processing locations or physical machines or virtual machines so that you can continue to grow the amount of data that you work with. Now, traditional RDBMS systems are known for having consistency and availability and for having some difficulty, as I mentioned earlier, at the highest levels of partitioning. What the CAP theory says is that database systems can really only meet 2 of the 3 aspects of CAP theory. So this is where Hadoop comes into play because, as I mentioned earlier, the data that's becoming available for businesses and other companies is growing larger and larger and larger. So partitioning and the complexities around partitioning and the expense is causing companies to look at database solutions that support that aspect, and maybe they don't have a need for the other 2 aspects to be as fully implemented. So you might be wondering where Hadoop fits in the CAP theorem implementation. As I previously mentioned, Hadoop is designed for scalability. Now let's understand a little bit more about how that implementation works in terms of partitioning. First of all, it's important to understand that by default, Hadoop is designed to run on commodity hardware. So cheap servers, really, really old servers, I see this very, very commonly. So by default, you can run Hadoop storage on these cheap servers. It's also designed for partitioning in that it makes 3 copies of the data by default. And if any of the copies become bad because the hardware becomes bad or corrupt, you can just pull that old hardware out. And then when you put the new hardware in, the Hadoop file system will automatically manage that copy process. This goes to another property of Hadoop, which is flexibility or availability. Because it runs on commodity hardware, you can scale a Hadoop cluster nearly infinitely. And again, if you'll remember back to where the HDFS file system came from, it really makes a lot of sense. It was designed by engineers at Google originally to index the entire internet. So it's infinitely scalable. And in fact, it's really interesting to think about some of the major companies that are using Hadoop in the United States right now. The number 1 user is Yahoo, and the number 2 user is Facebook. And these companies obviously have huge data sets, and they're taking advantage of the cost saving that they get, scaling all that data out on commodity hardware. And of course, they also want high availability because it's their business to be online and available all the time. So you might be wondering, what kind of data is right for a Hadoop solution? When I think about data, I think of 2 kinds of data. I think of what I call line of business data. Now, what does that mean? Line of business data is usually transactional, and actually it's not a good fit for Hadoop. As you might remember from the previous movie, transactional capability is not something that Hadoop is really designed to work with. And again, let me use that same example, which was taking 2 changes to a database, in the case of a bank account database, where you do a debit to your savings account and a credit to your checking account, and you roll those together as a transaction. That is your transactional data. Another way to think about it is any of your data that deals with making money, because usually you want transactions around that. What I find is that a lot of businesses have wrong information about Hadoop, and they think of it as a replacement for a relational database. And it really isn't. It's a supplement. Your line of business data is going to stay in your relational database. As an architect, I really haven't encountered any customers for whom they don't need some kind of relational database. Now, that being said, there is another kind of data, and that data is behavioral data. This is the world of big data projects. And let me make some examples of this. This is data that will be batch processed. So in other words, processed as a group rather than individually queried. And it is often a great fit for Hadoop. So some examples that I've worked with are around, for example, healthcare. We have more and more information being made available from the devices we wear, our Fitbits and our other kind of monitors. And it makes good sense to integrate that information with other types of solutions, like a medical records or medical diagnostics. Medical diagnostics would be kept in a line of business system because they'd be transactional. You'd want to know which prescriptions you took, and you don't want to have any data inconsistency there. However, your Fitbit behavior, for example, might be just very, very large, and you might just want to have that all added up or aggregated. And if you missed a Fitbit walk or 2, it really wasn't that substantial. Because in the case of healthcare, when you're out walking and maintaining your fitness, that's going to be a behavior that happens, for example, every day, as opposed to visiting a physician, which hopefully doesn't happen very often, maybe once every 6 months. In addition to the volume of data, it's also the type of data. If the data is mission critical or line of business, you're really going to keep that in a relational database system. Behavioral data is a great candidate for Hadoop. So as an architect, when I think about the changing data landscape, this is a simplified diagram of the kinds of solutions that I've been building for customers. We take a look at their relational database systems, and there are often optimizations that we want to do before we begin a big data project, because you want to have a clean house in order of your relational data before you start something new. But notice the size of the circle for Hadoop. This is somewhat reflective of the amount of data that you'll be collecting. I know I just talked about a medical example. Here's another one. I've been doing some work in online education. Online education is really changing as it becomes browser-based, and you collect data around not only whether the student gets the answer right, but what the student does when they're working on the exercise in the browser. Think of different types of activities that a student would do. They would move their mouse, they would type something in a dialog box. All these activities can reflect how well the student understands the information and could be useful to the company that's creating the educational software. Now, I've included a circle for NoSQL because Hadoop itself is on a file system. And as we'll see when we get into the processing sections of this course, the processing of this volume of information can be really complicated. And sometimes it's helpful to put an abstraction layer on the top of it so that you can get actual usable information out of that big circle. And that is often NoSQL. Now, I purposely didn't draw any lines between these circles because sometimes the Hadoop information goes into a relational database, so some small subset of it, and then it's queried through relational methods. And sometimes it goes into a NoSQL database, and it's queried through NoSQL query methods. Sometimes actually just keep it in Hadoop, and you run these batch processes, and you take the output as usually aggregated text, and you take it from there. So there's all different methods of processing this data. But it is really important to understand that Hadoop is not a replacement for a relational database system. It's a supplement. And very often it comes with the need to also add a NoSQL system, which, yes, adds complexity. It's really critical to understand these two components when you're thinking about Hadoop solutions. So what is Hadoop? It consists of two components and oftentimes is deployed with other projects as well. What are those components? The first one is open source data storage, or HDFS, which stands for Hadoop File System. The second one is a processing API, which is called MapReduce. Most commonly in professional deployments, Hadoop includes other projects or libraries. And these are many, many different libraries. I think there's over 25 now. The ones I see most commonly and we'll be covering in detail in this course are HBase, Hive, and Pig. In addition to understanding the core components of Hadoop, it's important to understand what are called Hadoop distributions. So let's take a look at those. The first set of distributions are 100% open source, and you'll find those under the Apache Foundation. The core distribution is called Apache Hadoop, and there are many, many different versions. I think we're up to 3.4 as the time of this recording, and there are many minor versions. The Hadoop version release cycle is quite aggressive and is a consideration when you're implementing Hadoop. Most enterprises stay 1 to 2 full versions behind the currently released version because they consider the open source software to be immature and not ready for use in a professional setting. Because of this, there are several commercial distributions, and these are the ones that I work with my customers most often. How they differentiate from the open source distribution is that they wrap around some version of the open source distribution, and they will provide additional tooling and monitoring and management along with other libraries. The most popular of these are from the companies Cloudera, Hortonworks, and MapR. And we'll be taking a look at all three of these most popular commercial distributions in this course. In addition to that, it's quite common for businesses to use Hadoop clusters on the cloud. The cloud distributions that I use most often are from Amazon Web Services or from Microsoft with Windows Azure HD Insight. Now here's where it gets a little bit confusing, so let me clarify. When you're using a cloud distribution, you can use an Amazon distribution which implements the open source version of Hadoop, so Apache Hadoop on AWS with a particular version, or you can use a commercial version that's implemented on the AWS cloud, such as MapR on AWS. Not all commercial versions are available on all clouds. So that's a consideration when you're selecting a cloud-based Hadoop distribution. We'll also be taking a look at the Windows Azure HD Insight distribution as it's gaining in popularity, particularly with Microsoft customers. As a reminder, there are several factors that cause businesses to use Hadoop. Now let's take a look at potential Hadoop distributions. You can set up your Hadoop cluster in 3 different ways. You could use the open source binaries, you could use a commercial distribution, or you could use a public cloud. For this course, I'll be using the public cloud. Now there's 2 ways that you can set this up. Using infrastructure, or as I call raw VMs or raw Docker images, or using platform as a service. And this is the vendor provides you with your Hadoop cluster images and some sections of that Hadoop cluster. Let's take a look. Here we are at the Apache Hadoop main site. And you can see that you can easily and quickly get the binaries here. You just would click download. Now, it's almost ironic to say easily and quickly. If you're new to Hadoop, I find that this process can be quite daunting. And in fact, I really wouldn't recommend it for beginners, because even though there are some pretty clear instructions now under the Getting Started button, this tells you how to set up your single node cluster, I really do find it's much more convenient to use a quicker setup process. However, you can do this if you want to. Now, just to be complete, I'll also show you Cloudera, where many of the committers for the Apache Hadoop ecosystem work. This is a professional company, and as of this recording, they also have consolidated with Hortonworks. Now, if you click here under products, you can see that this is really designed more for enterprise solutions. And I don't think this is actually a great starting point when you're learning about Hadoop, because the products have multiple pieces of functionality, whether they are, as it shows here, a data hub, data warehouse, machine learning, so on and so forth. And I think it's important to understand just core Hadoop. Now, to be fair, Cloudera does offer some resources for beginning learning, but my particular suggested path is to use a PaaS solution, and the one that I find most useful is the one from Google, and that's under Dataproc. So Dataproc, as it says here, is under the Google Cloud. It's a service. It lets you provision Apache Hadoop clusters and connect to underlying analytic data stores. And you simply click the blue Create Cluster button and fill in the web UI here, and I find that on a small size cluster for learning, this will take less than 5 minutes to spin up and less than a minute or 2 to spin down. Now, it is important to understand that there's no free tier for this. And so you really want to be conscious of your costs, because if you leave it on, it can be very expensive. But in terms of time to set up, we're going to use in this course primarily the Google Cloud Platform. Amazon has an offering, it's called EMR. Also, there's offerings from some of the other cloud vendors. I just like the speed with which this one comes up and is able to be brought down. One of the confusing things about working with the Hadoop ecosystem is there are a tremendous number of parts and pieces, libraries, projects, terms, new words, phrases. It's really easy to get core concepts misunderstood. And one of the concepts that I actually didn't understand the first when I was working with Hadoop is Hadoop versus HBase. So I want to take a minute to talk about it because it's really important and really central to understanding working with the Hadoop ecosystem. As I've been talking about in previous movies, the Hadoop core ecosystem consists of 2 parts. It consists of a new type of a file system, HDFS, and a processing framework, MapReduce. So this is a visualization so that we can really start to understand the detail around the Hadoop file system. You can see that we've got representations of files, and there are 4 files here. And as I mentioned in a previous movie, each file by default is replicated 3 times in the Hadoop ecosystem on 3 different pieces of commodity hardware. So you can think of them as cheap servers. Another implementation detail that it's time for us to think about is the size of the file system. Hadn't mentioned this previously, but the file system is designed for big data. And so unlike a traditional NTFS file system or standard file system, the size of each of these files is much larger. Traditional file systems like 8K or some small size like that, The HDFS by default is 64K or 128K and is actually tunable in config files to even larger sizes. And these are often called chunks rather than files. So it's really important when you're planning your Hadoop implementation to think about how you're going to lay out your files. And you can natively process those with the MapReduce framework. And sometimes then you can just get the result using the batch processing. However, as we'll see in subsequent movies, the MapReduce framework is written in the Java programming language as a core or some other programming languages. And some customers who are working with Hadoop really don't want to query or work with Hadoop data at that level of abstraction. And I like to say that MapReduce to Hadoop is kind of like C++ to object-oriented programming. Sometimes working with Hadoop at this level of abstraction is effective. However, at other times, you want to work at a level that is more accessible by more people in the organization. It's common that organizations have a small number of application programmers, but a larger number of analysts. So one such solution is working with a library called HBase. The way that this looks is a wide column store. So you can see on the right here, you have a table with one ID column and then a data column. And there's really no requirement for any particular values in the data column. That's why it's called wide column. You'll notice as a point of detail here that columns 1 and 2 have a name, but not 3, for example. And columns 1 and 3 have a location, but not 2. Another way to think about this is it's called schema on read. So as we'll learn later in this course, that you will need to impose some sort of schema in order to query or get the information out, but not when you put the information in. And again, you might be curious on how this table is actually created, and you do use a create table statement, which will then perform an abstraction against the Hadoop file system so that you can then work with it in a kind of a quasi-tabular format. So understanding the difference between Hadoop and HBase is key and core to working with the ecosystem. A lot of people think that HBase or a query language for it, which is called Hive, is actually part of Hadoop. And although it often is in practical implementations, they are two separate things. So keeping Hadoop and HBase separate is an important implementation detail. So you might be wondering, what is the market for Hadoop? Because it's a relatively new ecosystem. And as you can see by this graph from Indeed website, the job growth in the Hadoop market has been exponential. And you can see it really started to spike up around the beginning of 2010 and then up again in 2011. It's just exponentially going up. Now, it's important to understand that there are different skills associated with Hadoop and Hadoop implementations. In this course, we're covering a lot that has to do with Hadoop developers, very light coverage of administration topics, and we're also covering Hadoop architecture topics. It's a rich ecosystem, and as you are focusing on learning Hadoop, these are the overall categories that the information will be presented. So developer, administrator, and architect. So as we continue learning about the Hadoop ecosystem, another concept that we need to consider is a Java virtual machine. Now, in the Hadoop world, Hadoop processes or execution activities run in separate JVMs. The concept of a JVM may be unfamiliar to you, so let me give a brief explanation. It's basically a process for executing Java bytecode in an executable program. So it's a little section of the program that runs. And in the world of Hadoop, it's really important because JVMs don't share state. Now, traditionally, in database processing systems, state is shared. And this is a different programming paradigm that when we get into the internals of the processing around Hadoop, which is MapReduce, it will be really critically important to understand. JVMs do not share state, and the different Hadoop processes run in separate JVMs. Another consideration that we'll be covering in this course is that JVM process for Hadoop changes from Hadoop version 1.0 MapReduce, which we're going to start by covering because it's kind of the basics, to Hadoop 2.0. There are substantial changes in the JVM implementation for Hadoop from versions of 2.0 and forward. And as of this recording, Hadoop current release is 2.5. As we continue our exploration of the Hadoop ecosystem, let's look more closely at the file systems that can be associated with the Hadoop distribution. The default is to use HDFS, which we talked about in a previous movie, accounts for larger chunking of the data. and is triple replicated by default. The HDFS file system has two modes for implementation: fully distributed, which will give you the 3 copies, or pseudo-distributed, which will use the HDFS file system but is designed for testing. But it is designed for testing and will be implemented in a single node on a single machine. As an alternative to HDFS, you can run Hadoop with the regular file system. This is called the standalone mode. And it's a great way when you're just first learning about the MapReduce programming paradigm. You're reducing the complexity by just working with your regular file system. And I'll be showing this in some of the demos in addition to showing HDFS. Alternatively, when you're deploying Hadoop to production, particularly if you're deploying on a public cloud, it's really common to use a file system that's on that cloud. For example, in Amazon, the S3 file system, or in Azure, the blob storage, which is similar to the standalone mode in that you are not using HDFS. You're using a regular file system, but using a cloud-based file system. Another consideration is to understand how the file system of choice for your Hadoop implementation and Java virtual machines interact. If you deploy Hadoop in single node, you're going to use the local file system and a single JVM for all the Hadoop processes. Now, I know I haven't covered all the various processes yet, but we'll be going there shortly. If you deploy in pseudo-distributed mode, you're going to use HDFS, and the Java daemons are going to run all the processes on a single machine. If you run in fully distributed mode, you're going to use HDFS. It's going to be triple replicated, and the daemons are going to run in various locations depending on where you choose to place them. This placement choice is an important implementation detail in a production workload. To give us an idea of what this might look like, here is a drawing showing some of the common daemons and how they're distributed. So you can see in this particular drawing, we're in fully distributed mode. We have 3 separate physical servers. On each server, we have various daemons, and they're represented in green. So you can see we've got task tracker on each one, and then we have a job tracker daemon that is actually implemented on a different physical server. In addition to that, we have some other daemons that control the data distribution, the name node and the data nodes. Again, it's important to remember that in a production situation, these are separate JVMs and they do not share state. So we've got a lot of background information about the Hadoop ecosystem, and it's time to take a look at it in its full glory. It's a little bit of a scary picture with all these boxes and components, and one of the aspects of working with Hadoop is understanding what's possible and picking the various components that are right for your particular business situation. So I'm going to take a couple minutes and go through the core components here, and we'll be hearing about them again and again throughout the course because it's a little bit overwhelming when you first see it. So at the bottom, you can see that we have HDFS, the Hadoop distributed file system, which we just covered in terms of files. Most commonly used, but as I mentioned in the previous movie, sometimes the file system used, particularly in cloud implementations, is actually a more standard file system like Amazon S3 or Azure Blobs, depending on the cloud vendor. But it is common to use HDFS. Sitting on top of HDFS, the second core part of a Hadoop implementation is MapReduce. Now you'll see another new term sitting on top in this diagram, which is MapReduce version 2. This is also called YARN, and YARN stands for Yet Another Resource Navigator. And we'll be covering both MapReduce 1 and 2 in this course. It is become standard at the time of this recording that MapReduce 2 is more commonly used, but it does build on top of MapReduce 1, so it's a good way to learn the processing framework. You can see in addition to this on the right, we have HBase, which we covered in a previous movie, very commonly used to be able to query out of a column store abstraction over the top of the file system. And next to that is Hive, which is HQL, or the SQL-like query language that is used to query HBase. There are other libraries shown here as well, things like Pig, which is a scripting language that's used for ETL-like processes, or extract, transform, and load. You'll also see we have the Mahout library, which is for machine learning or predictive analytics. We have Uzi, which is for workflow or coordination of jobs. And that works in combination with Zookeeper, which is coordination of groups of jobs, and we'll see both of those things. Scoop is for data exchange in between other systems, particularly relational systems like SQL Server and Hadoop. Flume is a log collector because Hadoop jobs produce a large amount of log information about job process because the jobs are run in batch, so they take time to run. And in this particular diagram, we also have Mbari, which is provisioning, managing, and monitoring Hadoop clusters. This is a representation of some of the open source libraries in the Hadoop ecosystem. There are actually more. These are the core libraries. Now, to contrast this, we're going to take a look at a commercial distribution. You can see for Cloudera's commercial distribution in the center is Hadoop, and that's assumed to be HDFS and MapReduce 2. Surrounding that is Pig and Hive. To the right, you see HBase. You see Hive up above HBase as well because it's both for metadata and for query. You see something called Hue sitting on top of that, and that's specific to Cloudera. We're going to actually take a look at that coming up here in just a couple minutes, and it's a graphical user interface that makes interacting with Hadoop information simpler. You also then see Oozie, which is workflow and scheduling. You see Zookeeper for coordination, and Flume and Scoop. It is an important consideration when you're selecting a distribution to understand which libraries and which versions of which libraries are supported by that particular vendor, being able to match the capabilities of the libraries with your particular business needs. In this section, I want to introduce the library Apache Spark. It's for in-memory distributed data processing. So functions conceptually similarly to MapReduce, but uses the memory of the workers in the cluster rather than disk primarily, although it can use both. The library was developed initially at UC Berkeley by a group of genomics researchers in order to be able to process their analysis for bioinformatics because they were basically wanted to speed it up and they were running out of disk space. And it's been many years in the making. It is now available as a top-level Apache project, as well as there are many commercial distributions. The majority of the committers to the Apache Spark open source libraries do work at the commercial entity Databricks. And so there is this connection between Databricks and Apache Spark that's not unlike the connection between Cloudera and Apache Hadoop. There is an extensive Spark ecosystem, many libraries. Apache Spark is a fast, general-purpose processing engine. It's compatible with Hadoop data, clusters, and the Yarn resource coordinator. You can process data that's stored in HDFS, HBase, Hive, or any Hadoop input format. Data can be processed via batches or streams, interactively, and increasingly with machine learning libraries. To give us an introduction to the Spark ecosystem, this diagram shows that at the core, there is an API that supports, as of this recording, a number of different programming languages and interfaces. These include Java and Scala, Python, SQL, and R. So Spark SQL and Spark R are the versions of those languages for the Spark ecosystem. And you can see sitting on top, we have Spark SQL, we have Spark Streaming, we have MLlib for machine learning, GraphX for graph computation, and Spark R. And really, this is just a subset. I am seeing a lot of active activity in the development community with emerging libraries. Some are vertical specific. I've been doing a lot of work in bioinformatics. I've seen genomic variant analysis libraries for Spark, for example, as well as I've seen libraries that are specific to verticals such as IoT. So we've been talking for a while about Hadoop concepts, and you're probably getting anxious to actually get started programming it. So how do you do that? There are a couple ways to get it, as I mentioned in previous movies. You can get the open source version here. And you see here's the main site, hadoop.apache.org. And you can actually download the latest version of the binaries and set up Hadoop on your own. It does take a substantial amount of time to download and set up plain vanilla Hadoop on a Linux box. So for the purposes of this course, we're going to use a virtual machine, which is a lot quicker to get started. But I wanted to show you where this site was. And before we leave the site, I want to tell you a little story about the yellow elephant. I actually had the good fortune to meet Doug Cutting in person, who is the primary developer of Hadoop. And he didn't tell me the story, but he tells the story. His son a young son, was playing with a yellow elephant when he was translating the Google open source information about GFS and MapReduce into Hadoop. And his son called his little elephant Hadoop. And so in the beginning, there was quite a lot of discussion about, is it Hadoop or Hadoop? And it's just simpler to pronounce it the latter. So if you ever wonder where the little yellow elephant came from, it was Doug Cutting's son's toy. So anyway, so if you wanted to get the open source version, you'd go here, but we're really not going to do that. We're going to look at various vendor distributions because they're much easier to work with. So the one that we're going to start with is Cloudera, and we're going to look at several of them. Now, to be clear, most of these vendors have a free version to try out, and then they sell an enhanced version. So when you're working with this, what you're going to want to look at is you're going to look at the products, and we'll look at the various vendors. And you can see, in the case of Cloudera, we have Cloudera Enterprise, which is something that you would pay for. I believe they have a trial version. But they also have Cloudera Express. And as we'll see in a minute, they have Cloudera Live. Cloudera Live is really a great thing to try out because it basically allows you to try some of the querying and the interaction with the data in a browser without having to deal with any setup. And it's a quick start tip. Most of the major vendors, Hortonworks, I believe MapR, have an in-browser option. Now, when you're setting up a Hadoop cluster, you have a number of different options. And I'm going to focus first on setting up for training. When you're doing it for production, it's really a different set of concerns. So first, you want to think if you're going to use a virtual machine image or a Docker image from a Docker file. And you want to think about if you're going to use a VM, you're going to get the image from a vendor such as Cloudera or such as Google, or are you going to make your own? If you're going to move that configuration with VM images into production, that's the more standard way to set up a Hadoop cluster. And so scaling is understood via well-known and published pattern. I don't say this lightly because this comes from production work I've done over the past couple of years, scaling out Hadoop and Spark. It's really complex. And I actually did some work on the Docker side, and I published on it. I've got some articles on Medium under my name, did some genomics scaling, and it really literally took months because we were in uncharted territory. Now, that doesn't mean that you shouldn't go out on Docker. The idea here is that you want to look at your timeline and look at your other business constraints. In our particular case with genomics, getting the cost down was extremely important. So using Docker images was more cost effective than using VMs. But the base image is going to be key. You're going to have to make it for the Docker file, most probably, and you're going to have to test and determine scaling patterns. However, like I said, and I started this movie, I'm getting ahead of myself. The reason I mention this is because I've seen a lot of testing or learning clusters end up in production. First of all, that's clearly not a best practice, but it's just something to think about if you're deciding between VMs and Docker images. So a lot of people will start, rather than using the Apache Hadoop open source binaries, with a vendor distribution such as Cloudera. Now, Cloudera has had a lot of changes to their community edition and their web UI, which is called Hue. So it may be different as the time of you're viewing this recording. It's really challenging to keep up with presenting what it is they're representing. And there's basically a couple different ways if you're going to try to use Cloudera's Community Edition for learning and to get started. So the first one is they have a training virtual machine image or a Docker image. They actually have multiple ones. When I was attempting to download that, as of this recording, it was around 7 gigs. So it's pretty big. It requires your VM or Docker tools are installed either locally or wherever you're running it. Also, Cloudera, you can see they've really been positioning themselves more towards enterprise solutions. So their products, if you will, have to do with common enterprise problems such as Data Hub. And so finding a starting version of a Cloudera product is a little bit difficult. That being said, I did find out in the wild something that I find to be useful, so I'll share it with you. A public shared playground appears to be still run by Cloudera around their Hue browser. Now, when I say shared, I really mean shared. It's one playground, and so it nothing is, guaranteed to be there. It's basically everybody has, it looks like administrator access. So it's purely for learning. You would want to put only dummy data out there. And I'll show you what that looks like. That's at demo.gethue.com. And the username is demo and the password is demo. I find this to be useful to learn some of the various libraries. And as we'll see when we take a look at it and when we get into the libraries, I'm showing it in this course because it's zero setup. You don't have to install in libraries, configure them. You can just, for example, go in there and run a Hive query or a Pig script without having to have any setup. And I find that to be useful. Despite these two aspects of working with Cloudera, either Cloudera Community VM or a Docker image or this community site, I tend to use the public cloud when I'm prototyping any Hadoop Spark work. And I tend to prefer Google Cloud Platform Dataproc, managed or a PaaS Hadoop Spark cluster solution. And the reason is just speed. Well, and also cost. It spins up, as we'll see, super fast. Amazon's EMR or Elastic MapReduce is perfectly fine, and I've had customers use it as well. It's just for training, it tends to take, 15, 20 minutes to spin up versus Dataproc takes 5 minutes. There are other offerings. I just haven't done work recently with them. Azure has HD Insight, and Alibaba has eMapReduce. So in this course, we'll be working with Dataproc when we're drilling into MapReduce because I just find it to be powerful and the quickest thing to spin up. So let's take a look. Here we are at the Cloudera site, and I've navigated to the download section, and you can see that you select a platform and you download your particular implementation here. Also, if you're going to go this route, you're going to want to go into the documentation and read the documentation for the particular VM or whatever you use. Also in this course, you'll see me demo using Hue. And so if you want to follow along there, you notice the credentials are demo. And again, I'll admonish you, this is a fully public site. So you'll see lots of other people's data on here. This is just for learning. But it is really convenient because as you can see, it's configured with all the major libraries. Now, this is set up from Cloudera, so there's some that are specific to Cloudera, like Impala. But you see we have Hive, we have Jupyter Notebooks, Pig, Java, Spark, MapReduce, Shell, Scoop, Solar SQL. And then to just expand this out, you can see we have a dashboard, scheduler, we have documents, files, tables, indexes, jobs, and an importer. So you could even import from files or databases here. Now again, do not put production data up here. This is fully public. It is a demonstration site. So the idea is that you can just learn about some of these libraries. Notably, I think it's really useful when you're learning about Hive and Pig because it has a interactive HQL, which is a SQL editor basically. And then you can see that you have your various data sets. Now you will get a lot of red warnings and errors because there are some throttling limits on this. And so if you have too many users using it, basically it's just going to stop for your particular query. So I'm okay with that for learning because if it stops, then I'll just restart it. I like the fact there's no setup here and it's quick and easy to use. So I'll be using it in this course for some of the libraries like Hive and Pig. And then just to be complete, let me go back here to Google Cloud Platform. If you want to go this route for the MapReduce sections, you're just going to set up an account. There's $300 in free trial credits for most regions, but I am not sure. I don't think actually the Dataproc is part of that. So when you create a cluster, as we'll do in a subsequent movie, it'll actually tell you per minute how much that cluster is. Usually it's just a couple dollars. Just make sure that you turn it off when you're done. So as you might be thinking, setting up development environment for Hadoop can be quite complicated. I found the best way to approach it is to break it down into steps. So let's do that here. The first part is you need to figure out how you want the Hadoop binaries to be accessible. So you have really a couple different considerations. The first thing is, do you want to work with the open source, plain vanilla Apache Hadoop binaries, or do you want to work with a vendor distribution? And usually we'll work with a free version or a developer edition. And the way you pick the vendor is, if you have a preference because you have worked with that vendor before, say Microsoft, or you think the vendor is leading in the market, as Cloudera is said to be by many analysts and consumers at this time, or there's a feature that the vendor has that you want to use. So you need to figure out which version of Hadoop you want. Once you figure out which vendor version you get, then you want to figure out which version number you want. And usually you want the latest stable release, which is 2.4 as of the date of this recording, but it does change very rapidly, so you should check the Apache Hadoop site that I showed in an earlier recording to see what is the latest version and what's going to work for you. And probably the most complicated part of this is to figure out which location you want to put your Hadoop cluster or server in for development. I've found that it's often faster and in some ways cheaper to spin up a Hadoop server or a Hadoop cluster on the cloud because, as I showed in the previous movies, it's just a couple clicks once you understand all the different options. And I have tried to do a local install a couple times, but I really ran out of time. It took more than a day the first time I tried to do it. So even though it's completely free to install the Hadoop binaries on a Linux box, it really is complicated, especially if you're coming like I was out of the Windows ecosystem, and time is money. One thing I will tell you, if you do decide to go with a cloud-based version of Hadoop, is the cloud vendors do charge you. Amazon Microsoft charges by the minute. It's really a common new developer mistake to forget to turn off a cloud instance, and you can run up a lot of charges. So you really want to make sure that you turn it off when you're done. In the middle here is the option that I most often use, which is I will get a local virtual machine because I don't run a Linux box natively. Unless I used Hortonworks, I would have to, which runs on Windows, I would have to have a Linux box for it. And I will usually use the Cloudera virtual machine on my laptop. In order to do that, I have to have virtualization software. So I'm going to show you the steps to set that edition up with a local virtual machine in a subsequent movie. Now, there are a couple more considerations on your development environment for Hadoop itself. The data storage. I find that when you're first starting, it's actually simplest if you just set up Hadoop as a single distribution, which uses the native file system, which might seem kind of like you're wimping out. You're not using HDFS. But as you'll see when we get into it, writing the MapReduce algorithms is pretty complicated, much less testing that code and debugging it and deploying it onto production. So when you're just starting, it's good to start with, I think, the simplest possible situation. Now, quickly, you're probably going to move to the pseudo-distributed model, which is a single HDFS file system on a single machine. I find that I very seldom use a full distributed implementation for writing sample code or proof of concept code. That, of course, I will do if I'm in a production situation. But I find that when I just get started, to set up a cluster of either virtual machines or a cluster of Linux boxes is kind of overkill for development. The other situation is if you are using the cloud, then you need to figure out if you're going to use HDFS in, let's say, Amazon EMR, Elastic MapReduce, or if you want to just use S3 in the case of Amazon, or in the case of Azure, if you just want to use blobs. And again, just like using the local file system, when you are developing on a local machine rather than HDFS, I do find that sometimes when I'm using a cloud-based distribution, I'd rather just use the cloud-based file system. So kind of a learning I've gotten over time in working with Hadoop that when you are in development, you don't always need to use the HDFS file system. The third consideration is which libraries do you want to have as part of your installation? Which of the features are you going to be writing code against? So the core is which version of MapReduce, 1.0 or 2.0. And because there's so much richness around MapReduce, I'm actually going to show both in this course. We're going to start with 1.0 and then we're going to move to 2.0 when we're writing our MapReduce jobs. You also want to consider which additional libraries. As you've seen in previous movies, it's most common to have Hive or Pig at minimum. There are a number of other libraries that modern developers will use, and we'll touch on those as we get into that as well. And then finally, you're going to need some developer tools. So we're going to talk about that in the next movie. What I'm going to use in this course to work with Hadoop is the Cloudera Hadoop Sample Virtual Machine. There are a couple considerations here. In order to work with this, you need to look at your operating system and get the appropriate virtualization software. Sometimes the virtualization software costs money, sometimes it's free. I'll be using a Windows machine with VirtualBox. I've already downloaded the VirtualBox software in preparation for setting up my VM. The next thing is I'm going to get the Hadoop virtual machine from Cloudera for Windows for VirtualBox. And I'll show you what that looks like or where you get it from in just a second. That machine will include Cloudera tools and samples. It's a developer edition. What I'll be working with is the Enterprise Edition, but for development. So it's important to understand that if you were to deploy that, you would have to pay Cloudera a fee for some of the tools that are included with the sample that you're working with. And then in a later movie, I'll be showing you how to install additional developer tools that I find useful to work with. Now let's take a look at the Cloudera site so you can understand where to download the virtual machine. Here I am in the Cloudera site, and I'm going to be working with their Quick Start VM. So you notice the VMs run CentOS 6.2, and they're available for these types of virtualization software: VMware, VirtualBox, and KVM. You'll also notice that all of these VMs require a 64-bit host OS. Now, if I click on the version dropdown, I do have access to older versions, and these map to older versions of the Hadoop binaries. But we're going to work with the latest and greatest thing here. Again, I just happen to be most familiar with Cloudera's distribution. You could use MapR, or you could use Hortonworks, or one of the other ones as well. This is just the one that I've used most oftenly. Now, to get it, I'm going to scroll down, and you can see that I download from here, and I downloaded the one for VirtualBox. So after you finish downloading your virtualization software, and I have VirtualBox here, and your VM, then you just navigate to where your VM is located, and then you double-click here on the Quick Start, and that's going to open this VM in VirtualBox. And you're going to go ahead and review the settings. So let's take a look and make sure that we have the appropriate capacity on our machine for the defaults in this VM. So it's a 64-bit, 1 CPU. It's using 4 gigs of RAM, so it's a pretty significant amount of RAM. And the rest of the settings look okay. So I'm going to say import. And now my machine is successfully imported. So I'm going to go ahead and click Start. And I have to unblock some features of the Windows firewall. And you can see now you have your virtual machine, and I'll go ahead and open the terminal, and I'll type in Hadoop version, and you'll see that we're working with Hadoop version 2.5.0. After you've set up your Hadoop development environment, you might want to consider adding other Hadoop libraries. Most of the time, you'll be adding these core libraries, and if you're getting a vendor distribution, they'll usually be included. But if you're getting the plain vanilla open source distribution, you'll have to remember to add them. So you usually want to add Hive, which gives you the ability to have SQL-like or HQL query, and that creates batch MapReduce jobs with that query. The Pig library, which is an ETL or an extract, transform, and load like scripting language that allows you to do ETL type of tasks. Data manipulation, for example, stripping, trimming, joining, that kind of stuff. And another common library that is frequently used is Impala. And this, like Hive, lets you use SQL-like queries, but unlike Hive, rather than creating batch processes, it's an interactive process that makes use of the memory in the machine. And we'll be looking at this in more detail as we get into the intricacies of MapReduce. In addition to the core libraries, certain business users will have use for some of the many other available Hadoop libraries. And I just pulled out a sampling of ones that I have worked with here. The first one is Mahout, or Mahout, depends on who you talk to and how you pronounce it. And this is a library of machine learning algorithms or predictive analytics or data mining, if you will, things like clustering and time series and decision trees. It's a very rich library that's used by analysts and statisticians. Two of the newer libraries that are causing a lot of interest are Spark and Storm. They're very complex, and I'll be addressing them in more detail in a subsequent movie, but both of them have to do with in-memory streaming or processing. At a high level, the difference between Spark and Storm is designed for complex event processing, and Spark is designed for in-memory processing of resilient distributed data sets. Soon we'll be ready to write our first MapReduce job. So we need to decide a couple more things before we can do that. We need to pick our programming language and also our development environment. So I'm going to be showing the majority of the samples in Java, which also requires the installation of the JDK. It is also common to have MapReduce jobs written in other OOP or programming languages. One example is Python. And increasingly, we're seeing bridges between data-centric languages like the R language, which is a statistical language, and is more frequently being used as there's interesting implementations of Hadoop data scenarios. Now, in order to work with these programming languages, although you could use a text editor, I prefer to use an IDE. So the IDE that I'll be working with primarily is Eclipse for Java, and you'll see that in the virtual machine. Now, Cloudera's virtual machine does include an Eclipse installation. Not all of the virtual machines do that. So Eclipse, of course, is open source. So when you're setting up your environment, whether it's in a virtual machine or on-prem, you will probably want to have some kind of editor. You can use a text editor, but it's just a lot more efficient to use a fully featured editor, especially if you're going to work with Java. Now, when I'm working with Python, I just prefer Sublime, so I might be showing that in some of the samples as well. And then when I work with R, I work with RStudio. All right, let's create our training Hadoop cluster using GCP Dataproc. The first time that you come here, you have to enable the API. It's a one-time, one-way switch. There will be a blue button, say Enable API. It takes a minute or two. Subsequently, the API is enabled for your particular project. This is my project name. And then using this interface, you can click to create a cluster. Now, of course, just like with any other infrastructure, you're going to want to have a script, and I'll show you how to generate a script. You can check into source control for reuse as well. The first thing, little tip I want to give you on the UI is all the regions that are available are on by default. So if I say none and I just turn on the one that I'm interested in, it's just going to be faster for me. So I'll just use this one. And then I'm going to click the Create Cluster button. I'm going to call this Demo. It's now going to show me these regions. And then in the cluster mode, I can select single node, standard, or high availability. I like to use standard because then I can see the distribution of the work. You could use single node, of course, but you want to be aware if you've got a new GCP account, there's a limit of 8 CPUs per region. So the default setting for standard would fail because it would require more than 8 CPUs. You can either do a quota increase to get beyond that, or you can set the configuration as I'm showing you here, which will use only 8 CPUs. So in this case, I'm going to have the master node have yarn on it, HDFS name node, and all the job drivers. And I'll scroll down. And you can see I'm using 4 CPUs here. I could set that to less if I wanted to. I do have on the Google platform the ability to have GPUs if I had machine learning workloads. So I could add GPUs if I wanted to. There's my primary disk size, and here's my worker nodes. So you can see that this is set up to use 4 CPUs, and I'm just going to change this so that I use only 2 CPUs so that I don't go beyond my quota. You can see I have 2 nodes, so that's one master node here that has 4 CPUs and 2 worker nodes that have 2 each. So there's the 2 nodes. And you can set this up on SSDs or standard persistent disks. Again, the configuration when you go to production is non-trivial. I'm just doing a really simple cluster here just to get us up and going pretty quick-like. You can turn on auto-scaling, again, a production option. Now, this is a little tip in GCP. You can enable access to the web interfaces, which I really do like to use for the various libraries. Now, in order to access them, you turn the switch on, and then the access security rules are set automatically. And then to select them, you click into Advanced Options. Scroll down. We're going to accept the defaults. I'll call out here too, this is the image that is by default. So it uses a Hadoop 2.9 as of this recording. Might be different when you watch it, Spark 2.3. And the options that you have on a GCP are Hadoop and Spark. This is different in other cloud vendors. Now, also you can do a custom image, which would be more typical in production. And then here's where you add your components. So I'm going to add Jupyter Notebook, and that does require Anaconda. Then I will also include Hive Web HCat. I'm not going to have Zeppelin because that's redundant with Jupyter, Druid, Presto, and Zookeeper. These are various libraries. The optional components that are available vary, depends on the cloud vendor. They're different on Amazon, different on Azure. So it can drive your choice of your managed distribution. So we've got some ability to add advanced security. We can do automatic deletion, which is important in production, set up our encryption. And then notice here, if I click equivalent REST, this is the REST if you're going to use this in a configuration for a Google deployment to automate this. Or if you wanted to use the command line, this is the G Cloud. and you could just actually run that in a Cloud Shell. So that's a handy thing to just save out of here so that you only have to click through one time. And then we're just going to click Create. Now, while this is spinning up, I want to point out that you'll want to have a bucket configuration as well, because you'll be interacting with buckets on Google Cloud Storage. So in this case, what I did is I just created a bucket called Hadoop course. And again, you can just go with the default permissions, the default encryption for learning, but this would be where your source data would be coming from. And so you would want to set appropriate permissions in any sort of production situation. And this would be addressed with gs:// Hadoop -course. Now, if you use Amazon, for example, for your learning, then you'd use something like S3. Azure would be blob storage. So coming back to this, I'm just going to pause the video until this comes up, and then we'll tour around so you can see what we've created. All right, you can see our clusters available. We've got some information about it. And now if we drill in, we can see we have a performance recommendation, important for production. Now I have run a couple jobs just to test out the cluster. I'm going to show you how to run one in just a second. In seeing the monitoring, we have some core monitoring around key aspects such as yarn, so yarn memory, yarn pending memory, HDFS, and CPU utilization. And we also have integration with Google Stackdriver, which is a great reason to use the cloud implementation. Because you can see in basically into your jobs. Also, you have a button to connect you to the logs, which are going to be really important. Now, in addition to jobs, to look at your cluster, you can work with your VM instances here. In our case, we have a master and 2 workers. Something I really like about GCP is you have this SSH client built right in, which really is fast. Again, when you're working with Hadoop, there's so many parts and pieces. Anything that you can get automated so you don't have to think about it is going to help you to learn faster. It's just really a tip. So this SSH client automatically transfers keys. This works on Google Cloud for any VM. And once you're connected, then you have a Linux terminal. So you can just PWD. Well, you could submit jobs this way, but Google gives you a web UI. So again, in the idea of using the web UI for faster learning, we're going to use that. They also have this configuration here. And then, of course, we installed web interfaces. So once we run a sample job, we'll take a look at those. Now, in terms of sample jobs, there's all kinds of jobs you can run on here. You can see that the cluster has the binaries for Hadoop, Spark, SparkR, so on and so forth. Now, there are a couple example jar files on the Google distribution. I found these weren't really well documented. So first of all, it may change when you actually run this. You might have to SSH in and look for the jar files. And second, I just want to show you what it looks like. So we're going to run a sample job that calculates the digits of pi. So there's no data involved in this. It's simply making sure all the nodes of the cluster work. So I've run this a couple of times, and I'll just show you what it looks like here. This one, you can see pi is roughly this, and the job output is complete. So in terms of the configuration, this calls for the entry point, the main class, and then the jar file. And this is the path to it, and then how many iterations, 1,000 in this case. So I'm just going to go ahead and click clone, and I'm going to call this hello pi 3, and then I'm going to submit it into the cluster. Now, while this is running, and this is taking about a minute, we're going to go into the cluster and then use some of these web interfaces that we installed so we can take a look at how this is running. So you can see the Yarn Resource Manager, and basically we have a couple of instances that succeeded. And really nice for drilling in, understanding, where the overhead is. So let's take a look at the Spark history server. And now in our application, we'll take a look at the event timeline, and you can see when the executors were added. So this can be really, really helpful in working with this. And if we go now back to our cluster and our jobs, we can see that this succeeded. Now, because this didn't interact with data, it's a little bit tricky to understand where the output is. And one of the sort of great new capabilities of working with Hadoop is having alternate clients. And a client I like to use is a Jupyter notebook. You might remember that we installed the Jupyter interface in the web interfaces. And I'll actually open it up here. And I previously uploaded a notebook. So you just click upload. Now I have the sample files for this course up on my GitHub repository, Learning Hadoop and Spark. And this is this same calculate pi example, but rather than being a jar file using Spark with Java, I used PySpark, which is a scripting, so Python with Spark. And I like this when you're iterating because, you just want to make sure that your script's working correctly, and then you can optimize it and turn it into a jar file. So a typical sort of optimization is maybe to do some scripting in Python first, test things out, and then, once you want to scale them, then maybe rewrite this in Java. You can see here the calculation sets the number of samples to 1,000, and then I have a procedure called inside that uses the random library and sets X and Y to random. And then the count variable is using the Spark context, SC, parallelize, and then it's calculating pi. And I already have the answer just saved here. Now, what does this look like in this environment? So we're running this on our Hadoop cluster. So we connect here, and I've already run it once, so I'm just going to go ahead and rerun it. I'm going to say run, and there's our answer. And of course, if we wanted to, iterate, this is live, so we could just iterate that way. So I really like this new metaphor of working with Jupyter notebooks in a Hadoop Spark cluster, and I will be using this sometimes in the course. So you can use the web UI inside of the GCP UI. You can use Jupyter if you install it, or you could SSH in. A lot of different ways to run these computational jobs on your Hadoop cluster. So we've traveled far in our journey of understanding Hadoop, and we're really at a critical juncture now. We need to start talking about the nitty-gritty of the programming paradigm, which is MapReduce. So MapReduce is really what has caused Hadoop to be such a sensation in the data world. So let's start diving in so that we can understand it. I'm going to think of it like an onion because there's a lot of layers to this. So we're going to start on the top and we're going to just keep peeling in to deepen our understanding. So first of all, MapReduce is a method of programming. It's a way of thinking and it's a way of approaching data problems. It was originally created out of research at Google, and it was designed to solve a single problem, and that is how to index or get meaning out of all the information that is available on the internet. There's two parts to MapReduce. I bet you can guess what they are, the map and the reduce part. So let's first think about the map part of MapReduce. Technically, you're going to be writing a function in Java that is going to perform some action on some data. That function, when MapReduce is run as a job, will be run on each node where the data lives. You might remember from our discussion about a production Hadoop cluster that an HDFS node is normally replicated 3 times. So yeah, the map function will go to each and every node. And while that might seem inefficient, if you think about the scale at which Hadoop clusters are run in production situations like Facebook or Yahoo, their need is to be able to process the data and to have high accessibility or availability of that data, and they don't want to mess with if a single node goes down. You might remember from our discussion on files that HDFS is self-healing, so if a node goes down, the map job will just be retried on another node that has that data. This idea of bringing the compute to the data, that rather than bringing the data to the compute that is running the map job on each node, is one of the keys to understanding MapReduce. Once the mapper functions run on each of the nodes, they'll take some input and they'll output something very simple, a set of key and value pairs on each node. The second part of MapReduce is the reduce part. Like the mapper, this will execute the reduce function on some set of data. Now, this is different than the mapper in that the reducer executes only on some of the nodes of the cluster. You might remember that mapper will execute on at least one node for each set of data. So really, in essence, all of the nodes. What the reducer does is it'll aggregate the sets of key value pairs on some of the nodes. And the output of the reducer is a single combined list. So I think it's important when we're learning new programming concepts to have a visualization, and I really like this one. So you can see that we have 3 nodes underneath the mapper, and we have various types of data, and that's represented by the various colors on the mapper. So there's 3 physical separate machines. Now, in reality, the implementation is probably going to be more complex because that's the minimum amount. Most production Hadoop implementations have, at minimum, 50 to 100 nodes, but it's more common to have several thousands of nodes, and the data is triple replicated, and that's really not shown here. This is just simply shown different chunks of data on different map machines. You'll see that once MapReduce runs, the output is sorted. Now, I didn't discuss up until this point the magic in the middle, which is called the shuffle and sort phase. The shuffle and sort phase, as you might expect, is quite complex and one of the key aspects of MapReduce. How do those lists that come out of the mappers get aggregated into the reducer? Is it an automatic process? Is it something that we have to write code for? Well, the reality is a mixture of both. And when we are writing our MapReduce jobs, we'll work both with the default implementation of the shuffle and sort, and also we'll learn in what situations and how we want to override those defaults in order to get better performance and for specific data types. As we continue to think about MapReduce, I'll remind you that there are 2 major versions of this programming paradigm. And I think when you're first getting started, it's helpful to start with version 1. Version 1 is really an implementation of what Google open sourced so many years ago that they had success with in indexing the web. It's really very simple and focused. It's not for every big data problem, but it's a great way to start. Version 2, which we'll also cover in this course, builds on version 1. So let's think about the key aspects of MapReduce version 1. It is extremely distributed and scalable and can be very, very inexpensive because it runs on commodity hardware. We've talked about this over and over with the HDFS file system. It's resilient because if one of the nodes goes down, HDFS is self-healing. And it really lends itself to parallel processing because, as we just learned, the map portion of MapReduce executes on each of the nodes, so it allows for great scalability. And the reduce portion then aggregates everything on up. So hopefully you're getting excited to start coding this. So let's talk about some of the steps. The first step is you're going to create a class to hold your MapReduce. Now, just like any other code, as you become more sophisticated about this, you're going to refactor and you're going to have separate classes for separate pieces of functionality. But in our samples, we're going to keep it really simple and, just really straightforward. So we're going to create a single class that has the map class, the reduce class, and a main function with an implementation of a job runner, which will then call an instance of the map and reduce classes. Now you'll notice that I put static here. You might not be familiar with that if you're not a Java programmer. Static just means global. So parts of this programming paradigm is that the mapper and the reducer have to be static. So here's some pseudocode to get us warmed up. So if you're unfamiliar with Java, we're going to take it slow and gentle. If you've got C# or C++, it should be not a difficult sort of transition. The code itself, I don't find too difficult. It's the programming paradigm, because really what this is using OOP code or object-oriented code, where we have objects and we have instances of objects and so on and so forth, but it's being used in a functional way. And I think that's where really the challenge is for so many programmers who come out of the OOP world, like the C# or the C++ or the Java world, to be able to write effective MapReduce code. And what I mean by functional is a type of code where state is not shared. You might remember back when I was discussing the different JVMs, the different daemons, that I emphasized the fact that the task trackers that run on each node run in a single JVM, and JVMs don't share state. Well, as I just explained, when we run the map function runs in a JVM on each of those nodes. So for most OOP programmers, they're used to being able to share state when they do data manipulation. For example, they could create a customer object, and they could continue to manipulate the object several times in several ways, and then just output the results when they're done. That kind of programming won't be possible in MapReduce. In MapReduce, it's a single type of input in, run your mapper, get your key value pairs out, run your reducer, get your combined list, and then go on to the next one. So what does that mean in reality? What that often means is methods that you used in your relational database-backed programs will need to be split apart into several different steps, because you want to think of it as single input, single output. Very simplistically, you literally can think of it like functions in, for example, an Excel spreadsheet, where you have a set of numbers, you do a function or manipulation, and you get a new set of numbers, and then you go to the next cell. It is literally like that. So if we take a look at the code here, we've got our public class for MapReduce, and then we have our main function, and we would call a job runner instance, and we would call a map instance and a reduce instance, and we would have our map and our reduce, which would have a mapper and a reducer. So what is the hello world for MapReduce? It's called word count. And again, to understand it, we need to think about where MapReduce came from. It was Google trying to solve the problem of counting all the words on the web. So the example you'll see over and over and over, and you'll want to be familiar with as you're learning the different languages, libraries, and tools is Hello World. Now, it's a starting point. You want to go beyond there, but it's a great place for comparison. It's actually used for benchmark performance testing, like simplistic benchmarks, and it's just the de facto standard for getting started with Hadoop programming. So how does it work? Well, not a big surprise. It takes some text as input. It produces a list of words and counts them. So let's take a kind of silly example. I'm going to try to read this. Let's see if I can. How much wood could a woodchuck chuck if a woodchuck could chuck wood? Now, with a standard implementation of MapReduce, you can see the output after going through the mappers and the reducers. There's one word how, one word much, 2 words of would, 2 words of could, so on and so forth. Now, the key question looking at this is what constitutes a word? This is where you, as a programmer, come in because you're going to have to define that logic. There's no magic here. So a couple considerations just looking at this simple sentence. What's going to happen to the question mark? Are words case sensitive? Notice we have woodchuck, which is counted as a single word, but we also have the word wood and the word chuck. So what happens when you have duplication? These are all considerations around the logic of the implementation of the mappers and the reducers. To that end, let's take a look at some pseudocode for word count. So you can see in this word count MapReduce pseudocode, in the mapper, we have file name and file contents. And we have some kind of loop to iterate over the information. We're just using a for each. And here we have word in file contents. We want to emit that word and 1. So we're just splitting it out. Now you notice what's missing here, the implementation of what constitutes a word. What we're going to see as we get into the actual code is there's quite a lot of complexity here. It's very commonly implemented in a regular expression or some other kind of filter. And you'll see as we go along, this is a common source of errors, bugs, and also performance problems when we are scaling these mappers across hundreds and thousands of nodes. The pseudocode for the reducer takes the output from the mappers, which is a list of keys and values, and in our case, it's words, the words, and how many of them. And then we start with 0 as an initializer, and again, we have a loop. For each value in values, we take the sum, and then we add a value, and we admit the aggregated count. Now, there's other ways to do this, and again, we're going to look at the actual code in terms of correctness, effectiveness, and performance. Now we're going to drill into the details of MapReduce. First, we're going to look at some key aspects. MapReduce itself is an application programming interface, or an API. Physically, it's a set of libraries or jar files. So when we go to code it, we'll need to reference a large set of jar files, and I'll be showing you this in the demonstration coming up. The core components of MapReduce are the 4 shown here. The first is a job, which is a unit of MapReduce work. Now you'll create a job class, and then you'll also create an instance of the class in your code every time that you want to configure the running of the job. You'll also code a mapper and a map task. That will run on each node of your physical cluster. Additionally, you'll code a reducer and a reduce task, which will run on some nodes of the cluster. Another consideration is the type of source data and the location of source data. By default, it will be found in the HDFS file system. However, as I've mentioned in previous movies, it can be found in other locations such as a cloud-based file system, such as Amazon S3, or even in the local file system if you're running in standard mode. MapReduce works with several daemons and services, and it's important you understand how they work when you're writing your code that runs on them. Each one of the daemons is a separate JVM, and it's isolated. There's no state shared between them. So examples of these in MapReduce 1 are the job tracker. There's one per controller. It does scheduling. And then there are task trackers. There's one per cluster, and these are used to monitor the status of the executing tasks. In addition, you'll be writing job configurations. Parameters involved in this will be input-output locations for job instances, and these will be what the job clients will submit as jobs for execution. And these can be submitted in a number of ways, from the command line through GUIs and contained inside of other executing programs. I'm going to break up the slides of text with increasingly complex visualizations because I think balancing words with pictures is going to help us to understand the concepts behind coding MapReduce jobs. So if you take a look at this image, you'll see that we have 3 local nodes. Those are the dotted squares. And on the top it says input HDFS. So this is your input data. Now you're going to be coding or using the default input split. And you can see we've got split 0, 1, and 2. So there's 3 splits. It's a 0-based array. And then the map logic that you write will execute physically on each map node. And then there is a default sort mechanism, which you can override, and copy mechanism. This is also called shuffle and sort. And then there is a merge mechanism, which again, you can go with the default or you can override. That's why it's shown in white, because you can go with the default implementation. And then the reducer code that you write will then be executed on the nodes that have been selected to be reducers. All of these knobs and widgets, if you will, are tunable. There are defaults, and you can often accept the defaults and have perfectly acceptable performance, but in some cases you're going to need to tune or change these. And then you notice to the far right on step 5, you have the output HDFS, which are new files, part 1 and part 2, which will be replicated by default to a number of nodes. Do you remember how many? The default is 3 nodes. And of course, that also is tunable. Now, when you're working in development, I usually don't go to the trouble of setting up a multi-node cluster. I usually run in pseudo-distributed mode. And when we are working in the coding and the development environment that I've been using in this course so far, which has been provided by Cloudera, this is pseudo-distributed, so there won't be any HDFS replication. There are 3 coding patterns when you're writing MapReduce jobs. There's the standard pattern, and that's written in Java, and that's the one we're going to be covering here. There's also something called Hadoop streaming. It uses a Java base or framework, and it uses standard in and standard out piping. And then you can use other mapper or reducer logic. And this is commonly used by programmers who prefer writing their logic in a language other than Java. The one I most commonly see is Python, but you can also code your mapper or reducer core logic in something like C#. And there are several reference implementations out there. And then there is another coding pattern which I see used, which is called Hadoop pipes, and it uses C++. In this course, we're going to focus on the Java only. So now let's talk about running your first MapReduce job. As we learned in a previous movie, the starter program for MapReduce is word count. It's the equivalent to hello world in every other language. So there are many different ways to run this. You can run it in an IDE, you can run it in a runner, you can run it in the terminal window or in the command line. I like to start always in a graphical user interface because I think that there's a lot of complexity here. If we slowly peel the layers of the MapReduce onion, then we can understand without getting overwhelmed by onion fumes, if you will. So we are going to be using Eclipse and the Hadoop software development kit. Now the Cloudera VM is really easy to use because it includes both the Eclipse and Hadoop software development kit. If you're running the code in that environment for this class, then it's a pretty easy setup. If you are setting it up on your own, you're going to have to remember to download all the Hadoop SDKs and libraries. Now we're starting with MapReduce, but as the course continues on, you'll see that there are many other libraries that I reference. So it takes quite a bit of time to set that up. So I really recommend using the Cloudera VM or some other vendor VM like Hortonworks because it's just a lot quicker. As you run a MapReduce job, you will see the status update as the job progresses. What you're hoping to see is a successful completion message. And indeed, because that's so important, you will actually literally see the word success in the job output execution environment, whether it's terminal or whether it's a GUI or whatever. So you're looking for that word success in the output when you're first learning how to do this. Of course, you're also looking for the results of the process data. Now we're going to start with processing word count, so we're going to have some big body of text coming in. We'll have a series of delimited text files coming out, which will be a processing of that information. So these have a numbering scheme, part 000, 001, so on and so forth by default, which you can override. I want to remind you that HDFS data is immutable. So when you're running your jobs, you must configure a new destination location on each execution, because if you try to perform an update, the job will fail and say there's already data there. There is no concept of updating in HDFS file systems. Of course, if you're sending the output back out to the regular file system or to the cloud, you don't have this limitation and you can just rerun because it will overwrite by default. So you need to be cognizant of where you're sending the output and what kind of configuration changes you need to make so you can re-execute the job if you're going to do that. And usually what happens with the default execution in HDFS is you generate a new file name that contains a date and timestamp. And that's how you have uniqueness on the HDFS output. And as I just said, you usually append the runtime to the file name to create unique file names for output on HDFS. The next thing for us to think about is MapReduce job status and logs. Because MapReduce jobs can be very long-running, and in some cases too long, you might want to check the status and possibly restart them. It is a big aspect of working with Hadoop to have someone who may or may not be the developer who's going to monitor job run status. Now, in really large batch jobs, they may actually even run overnight, so you may want to set up an alerting system, and you can do that based on the tools in the vendor distribution. So this monitoring, we're going to look at it from a real lightweight status as we're developing MapReduce jobs. We're just going to look at it in the console. However, in production, you really are going to have some sort of more formal alerting system on your job run status. The open source distribution of Hadoop contains a couple of local websites which give you very simple job status application, and we don't see those in the Cloudera distribution because they've replaced that with their implementation, which is called Hue. It's a fancier website. You can always look in the log files. Now, reading log files is, as exciting as watching paint dry. So there's a lot of monitoring tools out there that will read the log files for you and then show you the anomalies. So oftentimes in production situations, you'll buy a tool to read your log files. Troubleshooting failed job runs is the job of both the MapReduce developer as well as the MapReduce administrator. And this is more so than in traditional relational database environments because of the volume of data that is generally run in MapReduce jobs. So you have a higher incidence of failures. So sometimes the admin will go back to the MapReduce developer and say, you need to fix A, B, and C. And sometimes the developer will say, this job's really running fine, so is there something that can be done physically on the cluster by you, the Hadoop administrator? There really needs to be a lot more communication than you're probably used to if you come out of a relational environment because of the complexity and the amount of data. And of course, when push comes to shove, if no one can figure it out, there are error logs that you can read. So there's execution logs and error logs. One thing that is very, very useful about the Hadoop API and MapReduce is that there is verbose logging that's output by default. Now that brings to another point. Perhaps you don't need that level of logging once you have the MapReduce jobs running on a regular basis because there is overhead for that logging. So logging in general is different than in the world of relational database data flow executions. It's more verbose. And so first of all, you should be aware of it. Second, you should plan time to interpret and understand it. And third, you should be ready to adjust the amount of logging, either up or down, depending on your needs. Because we're going to work with two different locations for files, and sometimes we do work directly with the terminal, although I like to use tools, I'm going to just take a minute and give you some tips in case you're new to Linux like I was when I first started with Hadoop. And so we'll start here. So these are your Linux shell commands or your terminal commands, and I'm actually going to show you a couple of them in just a couple minutes. So the first tip I'm going to give you is when you're using the terminal, you want to use your tab key because it's going to complete paths and commands for you. And here's some common file system commands. ls is going to list the contents of the current directory, the names of the files and folders. cat is going to read or display the contents of a file. So if you had a text file, it would read the contents out to the screen. Makedir is going to make a directory. cd is going to change a directory. Sudo, and then a command, means run as administrator or super user. chmod, some file, shows or changes permissions. There are a lot more, but these are the ones I commonly use in Linux. In addition to the Linux file system, we're probably going to use HDFS with Hadoop. So notice all these terminal commands start with the word Hadoop and then fs for the Hadoop file system, and then they're very similar. So for example, the first one, Hadoop fs -cat file, whack file, is going to read the contents of that file from the local file system. The next one you see is make a directory, but this is make a directory not on the local file system, but on the Hadoop file system. And then copy from local, that would be the local file system, put local file into the Hadoop location. And then here the next one, I've shown a sudo command, so run as administrator, running a jar or a Java file. And then I have an ls for a Hadoop directory, a cat reading the contents of a file from a Hadoop directory, file 1, and then a git. So the tips are, of course, sudo, which you find yourself using very frequently. And then some Hadoop configurations use Hadoop DFS rather than FS. So you just need to check your vendor documentation. In this section, we're going to work with file system commands in our cluster. I have some exercise files here in my GitHub, and you can use this to follow along if you want to. So the first thing we're going to do is into our cluster in the VM instances, we're going to SSH. And now make it a little bit bigger. And we'll first look where we are. So pwd, present working directory. And then we're going to go up a couple directories by cd space ... And now we are at the root. So now what we're going to do is we're going to navigate to a specific area by using cd. So we're going to go to the user lib spark examples jars, and then we're going to list the contents by using the Linux command ls space -la. And I'm doing this specifically because in this distro, Google has compiled the Apache Spark examples into a jar file, which is super handy for testing, and I actually use it in this course. So you can see the Spark-examples jar is aliased to the specific version. And I wanted to show you this in case this example file changes or moves. If you try to run it and the path doesn't seem to work correctly, you can just SSH in and you can look for it here. So now we're going to go back to the root location, cd space -tilde, and then pwd, and that takes us back, and then we're going to clear the screen. So now we're going to check the Hadoop version by just typing in Hadoop space version, and we're on 2.9.2 for this recording. And now in the Hadoop file system, HDFS or DFS, we're going to use a Linux command, but we're going to use the word Hadoop in front of it. So in the file system, we're going to make a directory, and I've already made it one called demo Hadoop, so I'm going to call it 3 for this particular recording. So make dir demo Hadoop 3. Okay, so then how do you see it? You basically use the word Hadoop in front, and then file system, and then you want the command. So ls. You can see I have 2 directories. Now, it's really important to understand there's 2 file systems here. We have the Linux file system and we have the Hadoop file system. The Hadoop file system, as you may remember from previous movies, has different characteristics. The block size is different. It's triple replicated by default. It's designed for the distributed compute. So it's like a layer of abstraction sitting on top of the host file system, if you will. So now if we want to work with this, if we want to pull in a file, we'll be using the Shakespeare file for word count. So we can cheat here and just upload this file this way. And this will be uploading it. So this is Shakespeare raw. And this file is available on my GitHub as well. That's a little text file with a Shakespeare play, basically. So now if we want to see that, we're just going to go LSLA on the regular file system. And you can see there it is, and it's in this developer directory. And if we forget which directory, of course, pwd, we're in the developer directory. So now what we want to do is we want to copy this from our directory into the Hadoop file system. And the way to do this with the command is using put. So let's take a look at this. So Hadoop fs -put. And I mistakenly hit enter there. The reason it exists is because we already have it in this directory. So what we're going to need to do, and Hadoop file system is immutable. So it's telling us, hey, look, it's already there. We are not going to write it again. So we want to put it into the directory we just created in the Hadoop file system, which is 3. So Hadoop fs put from the source, which is home developer 1, into the destination .demo Hadoop 3 Shakespeare raw. we've put the file up into this location, and I'm just going to type pwd. And now what I want to do is I want to see this file. So I'm going to type Hadoop fs ls for this directory. And that's going to show me the file. Now the last thing that I want to do is I want to read part of it, and we can use the cat command for that. Let me make sure I get the right directory here. So the command is Hadoop fs cat .demo, demo Hadoop 3, and the file is Shakespeare raw, and we're using the tail command because we just want to see the last 50 lines. We have to get the path right. And once I corrected the path, here's the last 50 lines. And again, the command in our case is just demo Hadoop 3. I had put it in a different location in a previous demo. So it's Hadoop fs cat demo Hadoop 3 Shakespeare raw. Now, in addition to working with the Hadoop file system, we will be working in a data lake pattern in this course. So we sometimes will use files that we put up onto HDFS, but more frequently, we're actually going to work with files that we put into a bucket in Google Cloud Storage. So you can see here I've uploaded the Shakespeare raw, and I've set the permissions to public by editing the permissions and adding all users read. So again, there's 3 different ways to work with the file system in these demos. One is, the local file system on your Hadoop cluster. One is the Hadoop file system. And the preferred way is going to be through working with a bucket. So a simple way to run a jarred MapReduce job is on our example GCP Dataproc Hadoop cluster. So I'll actually show you the process to do that now. Now, for testing, we're just using the web UI. Of course, in production, you're going to use scripts for this at minimum, and more likely, you're going to use an API and create a pipeline. But again, I'm getting a little bit ahead of myself. So it's really important when you're working with a jar file that has been compiled by somebody else that you understand the version of Hadoop this is designed to work with. If it's a different version, of course, it won't work properly. And you see that in the error logs. So the jar file that I'm using was actually part of the distribution for this GCP Dataproc cluster. It was on the image. What Google did kind of nicely is they took the Apache Hadoop samples and they built an example jar file. So I have set this demo cluster up again, and then inside of it, to create a new job, I can just click Submit Job. So I would call the job word count. I would select the region, my cluster. It's a Hadoop job type. I would need to enter the main class or jar file, and do be aware that this is case sensitive. And then if there were any arguments, and in this case, there will be 2 arguments. The arguments will be where is the source file that's going to be processed or the words counted. Now, there's a couple different ways you could do this, of course. If you were working with a Hadoop cluster that you wanted to work with the local file system, as we saw in the previous movie, you could just upload the file and interact with the local file system. Alternatively, you could use the HDFS file system that was available using the Hadoop fs commands, as we just saw. Or, kind of the more modern way to do it, is you bypass those file systems in favor of the object store or data lake. And that's actually what I'm going to show here. We're going to use the GS command in the path, which is Google Cloud Storage, and we'll point to our source Shakespeare file that's in a bucket that we've uploaded already. And then the second argument that this takes is it needs an output location. I'll remind you that the idea here is that these systems are immutable. So you would have to have some sort of programmatic logic to increment the name of the object, usually with the time or some number, if you wanted to run this more than once. Because if you ran it a second time, the output would already exist. And then you would need a path to the jar file. And this jar file is found on the image. And again, I just showed in the previous movie that you can SSH in and you can actually find it. So cooking show style, I did already run this. And so in the jobs here, you can see that the main class or jar file is org.apache.hadoop.examples.wordcount. The jar file is located as of this recording in this location. And do note that it has a version number. The version number might change to 2.9.2. The 2 arguments here are pointed to my bucket. So I have a bucket called Hadoop course, and I have the input data, Shakespeare Raw, which is a text file in one of Shakespeare's plays, and I have an output directory. So I ran this on my cluster, and you can see it took 49 seconds. I'm with a cluster with 2 workers, and you can see here is the map and the reduce jobs working. And you can see the job output complete. Now, where will you see the results? Well, you're not going to SSH into the Hadoop cluster because, as I was saying, we're using a data lake pattern here. So you would go out to the bucket and you would see here's the input data, but importantly, here's the output data. So we have this output directory and we get the success message, which we're looking for. And then if we want to download and look at the results, we can take any of the parts and then we can open them up in a text editor, and you can see here's our word count. So a nice thing about working with the job interface inside of here is that the jobs are saved for Dataproc. So if you turn your cluster on and off, as you probably will, it's a best practice when you're studying, what will happen is the jobs that you have run on Dataproc will persist. And then if you want to run them again when you start a new cluster, all you do is you go into the job and you go to the configuration and you click clone. And then what that will do is that will copy, and you have to give it a unique name, that'll copy all these parameters. Now, of course, you'd have to give it a unique name here as well, because like I said, it can only write one object with that name in your particular destination. And then you would just click submit to run it. So it's a really simple to use interface in terms of testing out jobs. One nice thing I like about the GCP UI is it has this scripting built in. So in terms of REST, this is the REST for this particular job. If you wanted to script through a REST API, you also can use gcloud as well. But when you're first getting started, I really like this jobs interface. It's just really useful to quickly run jobs for jar files that will be running Hadoop jobs. As we continue learning about MapReduce, I want to add some more context to our visualization as we get ready to start coding. So we see that we have input starting on the left side. And the first step is going to be splitting that input so that it can be chunked or processed physically onto each of the map nodes. Now, there is a default method in the MapReduce API that you can use, or you can override it depending on the type and size and processing that you're going to be doing to the data. Then the mapping code will execute. You, of course, write the map method. The shuffling is done by default along with sorting, but can be overridden if business needs necessitate. Then the reducing code is executed based on your logic, and the final results are aggregated. You also write that code. So if you look at the diagram, the code that you're going to be writing for every MapReduce job is the mapping logic and the reducing logic. Optionally, you can override the default implementations of the other phases. The MapReduce ecosystem is evolving. You may remember from earlier movies that MapReduce itself is more than 10 years old. So version 1 is very commonly in use. It's been out there for a while, and it's under the top-level library org.apache.hadoop.mapred. Version 2 has been out for a few years and is slowly starting to be the standard. At this time, however, you're going to see production code in both versions. Now, some parts of the API are almost identical, and some other parts are quite different. So we're going to start with version 1. But again, this is just a tip when you're looking at sample code. If you see org.apache.hadoop.mapreduce, you're looking at version 2. So you want to be really careful to not mix your code and to really understand and research which version you want to work with in both proof of concepts and production environments. So in addition to the MapReduce API, if you're using HDFS or really any other parts of Hadoop, you're going to have some other libraries. And I've listed the core libraries here. You can see that they all start with import, org, Apache, Hadoop, assuming Java for the import. And then we have the file system paths, the config, the IO, and the util libraries. These are really common libraries, and there are more that you might use, many more actually, but this is kind of like a baseline. Now, because I tend to write only with MapReduce 2 code, but I wanted to start this course with MapReduce 1, we are now going to review the code used to write a MapReduce job with the version 1 of the API. And we're going to break it down part by part. So we're going to start with the map class. So I want to point out a couple of things here. You can see the class is static, as I mentioned in previous movies, and it extends the MapReduce base. You'll notice that the types are familiar but different. So we have the mapper taking two text types, but two types that have the word writable, long writable and int writable. And as we delve into this, it'll become clear why. Then we have private final static int writable initialized to 1. And then we have a private text, word, new text. This is our key and our value. You might remember for word count, you have a value of 1 for each word that we find. That's what the int writable is, and the text is the actual text of the word. So now in our map method, public void map, we have a long writable, which is the key, and a text, which is the value. Then we have an output collector, which takes a text and int writable output, and then in this case we use a reporter for status. And then we throw an exception, a file exception if we can't access the file. Then we have a string align the value to string. And then here we have an interesting utility class, string tokenizer. And we create an instance of it against the line. So what does this do? This is one of the utilities in the MapReduce API that breaks down words. Now, if the default method of breaking down lines into words is adequate for your business case, you can just use a string tokenizer. But many times in production situations, you have to extend or perhaps replace because of either performance or the logic isn't exactly what you're looking for. Maybe you have foreign characters. Maybe you have some considerations that the default string tokenizer doesn't take into account. Then you have a while loop. While the tokenizer has more tokens, then take the word and set the tokenizer to the next token, and then collect in the output collector word and 1. So what this does is this runs on each one of the physical nodes, and it takes the chunks of text from the HDFS file system by default, and then breaks them into a set of key value pairs, the text of the word and the number 1. So next part of this is the reducer code. So again, we have a public static class reduce, which extends the MapReduce base, and it implements a reducer, taking text and int writable and text and int writable. And it implements the public void reduce method, taking text key, an iterator of int writable, the values, the output collector of text and writable, the output reporter, and throwing the file exception. It creates a variable called sum with an initial value of 0. And then we have a while loop. So we look at the values and we run the hasNext method. So then we take the sum value and we plus equal, which is sum plus the values, next get, and add it to the sums. It's a collector. And then we pass that output collect, the key, new int writable, the sum. So what that means in English is we're aggregating or we're counting up the number of words of each type. To run this in MapReduce 1, you write a main method, and inside of it, you create an instance of job configuration or job conf, and you pass in the word count.class. And then you set the job name, set the output key class, the output value class, the mapper, the combiner, the reducer, the input format, the output format, the file input format, the file output format, including the path, and then you run the job. It is this combiner class. It's called a local reducer. What it does is it performs an aggregation or adds up the keys and values on each node so that less traffic is sent across the network to the reducer. Let me make an example. Let's say you're processing some text. So you have the word the, and rather than sending the key and value, the one, 100 times or 1,000 times from each node, if you run a combiner, you'll send the 100, the 101, the 102, so on and so forth, the count of it across the network, which can really improve performance. Now, the interesting thing about the combiner is it's not guaranteed to run. It's an optimization. So it is optional, but it's a really common pattern, and so I left it in here. So the key components of the Java implementation of MapReduce are the input and output, and I deliberately didn't go very deep into the write and write comparable at this point. I'm going to do that coming up just in a minute here. And then we have the mapper, reducer, the partitioner, the reporter, and the output collector. Those are the key components. Now it's time to talk about those writable data types. You may remember that I talked about HDFS files as being immutable. So how do we perform looped aggregations? Well, we have special types, which are extensions beyond the base Java types, and they're required for MapReduce. So you can see them listed here. So you've got everything from a Boolean writable all the way to a long writable. And you can see that text doesn't have to be designated as a writable. All the numeric values do, though. And notice they're described as wrappers. They're wrappers for the Java primitives. Notice the last entry in the chart, your writable. For some situations, it makes the best sense from a performance standpoint for you to write a custom type. To do that, you would implement the writable interface for a value or the write comparable of T for a key. Notice you would also have to define a sort policy for your custom writable. So there's quite a bit of code to write, although there are some good samples out there. So what would be an example of that? Perhaps like a geospatial type, where you have lat long or some combination of point in space or time that doesn't aggregate or sort in a way that is natural for the primitive types. So as we're looking into the detail of MapReduce, another consideration is input types. So you can see in the table here that I've referenced some of the most common ones from text, key value, sequence file, and end line, and just giving you a little bit more detail. And this is just based on, again, my experience in working with Hadoop in real-world situations. Text is obviously the default. So it gives you the description of it. Each line in text is a record, and the key is a long writable, the offset of the line, and the value text is the content of the line. And again, the main reason that I gave you this information is so that you can determine if you can use pre-existing types or you need to provide some additional business logic or do some pre-processing on your input into Hadoop. And just to contrast text input, let's just take the next one, key value text input. Each line is a record. The first separator divides each line. The separator set by key.value.separator.in.input.line property, the default is the tab. Key is text is anything before the separator. Value is text, everything after the separator. So again, these implementation details are really, really important when you're writing your MapReduce job. So you're going to need to dig in and look at not only the default input types, but you're also going to consider what is the data coming in, what kind of pre-processing, if any, do you want to or need to do, and how might you need to override or use different kinds of types than the defaults if you're unable to or just doesn't fit your business scenario to make any changes to your incoming data so it matches one of these input types. As with input types, I wanted to talk a little bit about output types. So I put some of the most common ones here. So you have the text output format, which is key value, the sequence file output format, or the null output format. So the text writes each record as a line of text. Keys and values are written as strings and separated by a tab, which can be changed in the MapRed.TextOutputFormat separator property. The sequence file output format writes the key value pairs in sequence file format. It works in conjunction with the sequence file input format. So if you change one, you change the other. Now the null output might seem really, really strange. You might be surprised to see the null output format, but there are business conditions that warrant that. So now that we've run our first few MapReduce jobs, let's talk about the different ways that you can run MapReduce jobs. In production, you're going to configure your job comp options. You're going to set things like timeout values and paths for the output, paths for the input for the data. For us as developers, we won't often use those complexities. Rather, we'll work from our IDE or our coding environment, and we'll usually either just create a jar file in our coding environment and then run it from a command line, or we could actually use unit testing framework and just stay within our coding environment. But I did want to show how a MapReduce job is actually run in production because I think it's important to understand the destination when you're writing that code. Now, I usually run my MapReduce jobs in a GUI utility rather than from the terminal because it's just a little simpler and has richer output. So I showed Cloudera Hue. If you use a different distribution, like, for example, Microsoft Azure HD Insight, there's a rich console you can use. Most of the commercial vendors have a lot of instrumentation and monitoring around job execution because that's the core part of actually running Hadoop in a production environment. Just as a reminder, from the command line, you would issue the Hadoop jar command, and then you put the file name for the jar and the input and the output locations. Now, in terms of job execution optimization, A common paradigm is called speculative execution, and what that will do will kill long-running jobs based on configurable parameters that you set, either in the source code or more commonly in the execution environment. In, for example, Cloudera Hue, you can specify the overhead it takes to run a job, the number of mappers, the number of reducers, so on and so forth, so that a job can be automatically killed if those values are exceeded. This is a common situation in production code, so I wanted to include it here. Now, we're going to come back to the world of being developers, and we're going to dig into methods to write MapReduce jobs. We saw an example of the Java code for the MapReduce 1 API, and we're actually going to write from scratch a MapReduce job using the more common MapReduce 2 code coming up here shortly. The standard way to write a MapReduce job is in Java, and I usually use Eclipse, although you could use something like Vim if you wanted to. Some people prefer to write MapReduce jobs using the streaming paradigm, where they start with a Java scaffolding, and then they use the standard in, standard out methodology, which is like a piping, and then they can write the logic of their mapper or their reducer in their language of choice. And I see things like Python or C# or even JavaScript. Pipes is another method to write a MapReduce job, and the most common language that's used with that is C++. Now, in addition to traditional programming languages, there are a whole wealth of abstraction libraries that I'll be covering in this course that a lot of people prefer to use because they're more fluent in these particular languages. There are things like Hive, which uses a ANSI SQL-like syntax that allows you to write in a database query-like language, and then it will generate the lower-level MapReduce. Pig, which is a batch language that's used in extract, transform, and load processes where you're actually doing data cleansing. It's really common that people will prefer to work in a higher-level language, but I do think it is important that you understand at least something about the internals of MapReduce because these languages do generate MapReduce jobs. In fact, this just gives you an idea of the wealth of languages and libraries I see around the Hadoop ecosystem. So one of the tips that I would give you is you want to figure out at what level of abstraction you and your team is comfortable working with the MapReduce paradigm. If you have a group of OOP programmers at your disposal, then you may want to work with Java. Even if they're C# programmers, it's pretty easy translation. If, on the other hand, you're surrounded by mostly business analysts and you really don't have too many programmers on staff, you might want to focus on higher-level languages like Hive or Pig or some of the other ones. This is a really important architectural consideration when you're implementing Hadoop in a production situation because you really have to have the appropriate level of understanding of the language so that you can implement the data processing paradigm in a way that's going to allow you to get value out of all that data you're storing in HDFS. So let's consider our visualization when we think about the possibilities for tuning MapReduce. So again, we see that we have 6 different places where we have the opportunity to tune. Now we're going to start in this section and talk about physical tuning. There's a lot of tuning that we can do through our MapReduce code, but it has to work in conjunction with physical tuning. And this relates to physically what the data looks like when it comes in, where it lives, what's the capacity of the system that it's being processed on, what's the connectivity to the output location, and the capacity of the output destination as well. So you can think of it as a cycle. So you can do optimization on the upper right before the job runs. So what are some kinds of optimizations that I've completed before jobs run? Well, I mentioned it earlier, but I'll call it out again. The most common one is pre-processing on the data. So what does that look like? I might take text data and do something like remove all the non-English characters, remove all the punctuation, or do some other type of parsing just to make the actual MapReduce, if, for example, I'm analyzing the words for maybe sentiment analysis, a little bit faster and easier. So pre-processing on data is a common optimization task. Now you can also optimize on load of the data. How you might do that is you might change the compression ratio, for example, so that the size of the data is actually smaller. You might break the data into different sized chunks. You might change the scalability of the data load. This is particularly an option if you're using cloud-based Hadoop scenarios where you can spin up additional data nodes and spin them down quickly and cheaply. Then you're going to optimize the map phase of the job, and that usually deals with code and how you write the code. So we'll look at that in greater detail in another movie. You can also optimize the default shuffle phase of the job. That's a highly complex task, And it's something that in production I've only seen a couple of times. So my recommendation is to let that execute in the way that it's designed unless you have a very compelling business reason to make a change to it. You can then optimize the reduced phase of the job. I see this happening less frequently than the map phase. I'll be giving you some techniques in subsequent movies on how to do that. And you can also optimize after the job completes. Now, what could happen there is you could take a really bulky job and you could break it into two jobs so that the first job was more lightweight and processed more quickly and possibly using greater parallelization so that the second job could process in a more timely manner. You really want to think in terms of chunks or Lego bricks when you're thinking in terms of MapReduce design. So I talked about optimization before running a MapReduce job, and I talked about a lot of the items on this page, but I'll just make sure to be inclusive. So I talked about compression, using a compression algorithm that's most optimal for your situation. And compression is a balance between how much compression you can get and how that compression affects the processing. If in your mapper you have simple logic, you can take advantage of a high level of compression. However, the opposite is also true. If you have very complex mapping logic, then sometimes you need to go with a more lightweight compression. Now, I didn't mention encryption. For some data, encryption is part of the business rules. You have to consider the overhead of working with encrypted data, which sometimes will entail de-encrypting it and sometimes won't. When we think about physical MapReduce optimization possibilities, the number one thing that I see out there in the wild is that the cluster configuration parameters have somehow been changed and there's not a good business reason for those changes. People are just trying things out and it's not documented. And what happens is on different MapReduce jobs, because we have non-standard configuration parameters, there's unexpected behavior. So if you're going to change from default cluster configuration parameters, make sure you have, number one, a compelling business reason. And an example of this would be if you want to change from the default replication of 3 nodes for each piece of data in HDFS to some other value, 2 nodes, no nodes, 5 nodes, for example. Have a compelling business reason for doing so, and make sure you document that so anybody else working with the cluster can understand. Another thing is you should take a look at both unused resources, so data nodes that aren't used during the majority of your MapReduce jobs, or overstressed resources, data nodes where you have a lot of spillage because your map processes can't fit into memory on all the data nodes. They spill out to disk, which takes a lot longer. From the highest level, are you using any sort of cluster monitoring tools? Now, we've seen in the Hue interface that we have lightweight monitoring, but this is part of the value proposition around the vendor distributions. They provide really industrial strength cluster monitoring tools that help you get the best value and the best performance out of a Hadoop cluster, and they're really worth investing in. One of the ones that I've looked at is Ganglia. There are many out there, tens if not 50 of them. There's a lot of different companies working in this space because it is complex, and you do want to make the appropriate use of the physical resources in your cluster. It's very easy, obviously, in a Hadoop cluster to just add more nodes, but you want to do it in an intelligent fashion and make sure that those nodes are actually being used because of the configuration settings and the MapReduce jobs that you're running through your Hadoop cluster. And I mentioned it, but the simplest possible optimization is to add more nodes. So again, you don't want to overlook the obvious. Hadoop is designed to scale. So especially if you're using cloud-based implementations, I find a really effective optimization technique when you're running against time deadlines, and maybe you have changes in your staff, so you can't rework your MapReduce jobs, some other complexity, just spin up more nodes. Another variant of this is if you have an on-premise cluster and it's getting stressed, and you really don't want to go out and purchase some more hardware, you can augment on-premise clusters with a partial implementation on the cloud. This is a sophisticated use of Hadoop, but I see really smart companies doing this where they'll offload some of their one-off batch processes. I've done this with some companies that process genomic information. They have the initial processing of the large amount of genomic information, which they need to aggregate and compare. They'll push that off onto an Amazon Hadoop cluster and use spot pricing, as I talked about earlier. And they can get a really cheap and effective, quick process of a lot of data, and then they can pull that data back down and they can work on it locally. So this idea of mixed, both local and cloud-based Hadoop is really coming into play, and it's something for you to think about when you're optimizing from a physical standpoint your Hadoop implementation. As we think about tuning a mapper, Let's trace through the path of data through MapReduce. So let's take a look here and start with the map. And the map will work with a key and a value. So let's call this key 1 and value 1. And that's going to be your info coming in. And how that comes in is going to be dependent on the data type and the default input split. That will produce, once the map logic runs on each node, a list of key 2 and value 2 pairs. Those are called intermediate values. There's going to be one list for each local node. By default, if we did something like a word count, it would be the word and then the number 1. So the 1, man 1, is 1, at 1, home 1, like that. So it's quite common in these types of situations to use an optimization that's called a combiner. What that is, it's a local reducer. What it does is it aggregates for each node, in this example, every instance of the same word. So if we had the word the 20 times, instead of listing it 20 times, we would have the 20. It would be a local combiner. Now, this is an optimization that is really commonly used because then less data is passed across the network. It's so common, it's almost standard. It's not required, but it's a really, really common optimization. Now, continuing on, once the output is run from the mappers, then by default, the shuffle and sort will run. And then the second part, of course, is the reduce. So looking very granularly on the right side, we've got the keys, and then we have a list of the values. And the reduce will combine the map output into a list, which will make a new list of K3 and V3. There will be some intermediate aggregation done, depending on the amount of processing that needs to occur and the amount of resources on the reducers. And again, there's opportunity for you to look into that process and to provide further optimizations. One of the things at a high level is always keep your jobs as simple as possible. And if you feel like they're getting too complex, break them into 2 separate jobs. Back in an earlier movie, when I introduced the idea of MapReduce, I talked about the difficulty for OOP programmers getting their head around the MapReduce programming paradigm, which is really functional programming. One activity should be occurring, not 5, not 10, not really even 2 or 3. One type of process. So take the example of word count. In the mapper, we receive the text input, we parse it line by line, and we split that text into individual words based on some methodology. The default tokenizer uses spaces. You can write your own, as we talked about, but you have some sort of logic. Now, if you had to use complex A, B, and C, split, and then add, and then divide, and then manipulate, those should be separate MapReduce jobs. You can chain them together. It's a different way of thinking, but it's really the way the MapReduce API was designed to be used. So when we think of mapper task optimization, we have many different things that we can look at. The first thing I already talked about, which is subdividing tasks. That's the most common thing I see out there in the wild, where you need to break your mapper apart into separate mapper tasks. And as I said, you want to aim for really no more than 1, 2, or 3 processes to occur. And really it should be short. That should correlate to minutes, 1 to 3 minutes per map task run. Now, there's many other things that you can do in addition to this to optimize your mapper. You can, for example, set up a custom partitioner. The default is a hash partitioner. You can override that. You can partition by any value that's being passed in. That could be a numeric value, it could be a text value, a binary value, anything at all. Another optimization method is to reduce the amount of data. You can include logic in your mapper to skip those records that are determined to be invalid or bad. In your mapper, you can define what constitutes a bad record, and then you can also include a counter, and you can set a value at which the map job will stop or retry if too many bad records are found. You can also use this to assist in debugging or unit testing. Another optimization is you can monitor and tune for optimal spill ratio. So spill ratio means when the memory on the mapper machine is overloaded and the processing has to spill out to disk. That's what the definition of spill is. So the spill ratio is how many records spill out to disk versus those processed in memory. So the goal is the number of spilled records will equal the number of map output records. And you can tune this in io.sort.spill.percent. And you can also set the desired number of mappers in the config files. I've already mentioned local reducers, which are combiners. Another optimization that you can do is you can set map-only jobs. no reducer. What's an example of this? Because this is a little bit strange when you first hear about it. One that I've seen is photo processing, where you pull in images and you pull them in as binary and you do some processing on them. And then when you're done with each map process, you simply pass them through because there's no aggregation that's needed. You're doing some sort of processing on each photo in this case. So let's look a little bit more deeply at input file compression. And I'm just taking what Cloudera uses. Vendors are different, so you're going to want to look at the vendor documentation. You really want to read what they recommend because their distributions do vary in how they support the different compression algorithms. So for example, in Cloudera, their version of LZO is splittable. So that compression algorithm you can write a custom input split for if you want to further segment the files. You always want to use the most efficient compression for your particular vendor or distribution. And I have a little chart here on the bottom that shows from Cloudera how much you can zip, what the size is, and what the decompression size is. As we're talking about compression, I want to remind you thinking about data types in terms of mapper optimizations. You know from the code sample that we saw earlier that we need to work with writable types. So when we work with writable types in our mappers, we need to think about how the information is being compared and also sorted. Custom types are supported. So if you're not getting the performance or you're not getting the business logic out of the types that are available, you can create your own type. Now there's quite a lot of code that you'll be writing for that, and you need to write a comparator. So an example of this would be geospatial data types. You need to test the performance of your comparator because, again, this is your logic, and you haven't had as much experience writing MapReduce code as the people from the open source community. So just, again, based on my experience, if you're writing your own type, you want to test with production levels of data the comparator function that you write. It's called a custom comparator, and often you'll also want to write a custom input split. Because if you think about it, if you have geospatial data, how is that going to be split? It'll be split by default as if it's numeric data, and that might not make good business sense, particularly if you've got clumps of data in different geographic regions. Let's say you're a U.S. company and you do most of your business in New York and California. So if you split your data by the default method and you had a geospatial type, that really wouldn't work well when you were loading for MapReduce because you would not make maximum use of splitting the data across all your map nodes. You can also write a custom partitioner. Another tip I'm going to give you around data types is you only want to use the text type when you're using text data because there is a slight performance difference between text and the numeric types. And this comes out of recommendation from Cloudera. They see out in the wild that OOP developers tend to default to the text type even when they really should be using a numeric type. While it's not as common to decide to do customization around the reducer phase of MapReduce, I do see it out there. So I'm going to talk about what I see in my production situations. So reducer task optimization usually falls into 4 categories. The first thing is, just like we did with the mappers, subdividing. So if you see reducers being overloaded, possibly you're trying to have the reducers do too much work, and you should break this into a separate job and just run it straight through another set of mappers and then through another set of reducers, so job chaining. Another reducer task optimization technique is logging or debugging so that you can understand where the load is occurring. Because, of course, with the reducers, they don't run on every node of your cluster, unlike the mappers. They only run on some nodes. So you may need to dig into those logs to find out exactly which nodes your job is executing on, in which situations, which nodes it's not executing on, where the bottlenecks are occurring if there are clumps of data. You can add a secondary sort into a reducer job, but when I see that, I really usually recommend to break the job apart. I prefer to have small separate jobs chained rather than beefy jobs that are doing more than one task. You can also set thresholds in the configuration like you can in the mapper so that you can either kill long-running jobs, suspend jobs, get more information about jobs depending on the workload. So I have some more reducer optimization techniques. The first one is, from an architectural point, looking at the amount of work in your MapReduce job and saying, could part of this be broken into a separate job that doesn't even use a reducer? I made the earlier example of photo processing, and I actually do see that quite frequently. because more and more different types of data is coming in. It's not just text data. So sometimes this data needs sort of a pre-processing that's highly distributed. So photos is a common use case. I've seen sound files or music files that need to be pre-processed, and they're just running map-only jobs. And then they're pulled into a secondary chain job to do the map and then the reduce. Also, you can use local reducers, as I've been talking about. It's a common pattern called combiners that run on the map nodes, and they substantially reduce the volume of data in transit to the reducers. We have one last optimization to talk about, and that's creating a distributed cache. So what this is, it's used to cache files, things like text files, archives, jar files, that are needed to run applications or jobs. How you use this is you include the path to the file via a URL in the job configuration or job comp settings, and the paths can be to a location on the HDFS file system or on HTTP. The files will be copied to each data node on each job execution for the mappers and are often used in scenarios like lookups. This is found in this library, org.apache.hadoop.mapreduce.filecache.distributedcache. Now, let me take this example a little bit further. Let's say you are using a lookup as part of a map job, maybe something like a business identification code, and then you wanted the name of the business to be output in the key value pairs, and you had a master data file that identified all your businesses or all your customers by number. So that would be a common scenario for this. Now, we've reached the end of our tour of MapReduce job optimization for MapReduce 1. Add more nodes. Again, you want to go with the low-hanging fruit first. You use MapReduce and Hadoop because it's highly distributed and highly scalable. And if you think about it, although you can tune almost any knob or widget in the MapReduce algorithm chain, it sometimes takes a substantial, large amount of time to understand how to tune it properly. And it's just cheaper and faster to go buy more nodes. Now, that being said, that isn't always the answer. I generally start with more nodes, and then I will continue to profile to see where the bottlenecks are occurring. Sometimes it can be kind of a Band-Aid solution. Just like I said, go up on the cloud with some of the loads so you can get more nodes on the cloud and then come back down and see what's causing issues in your cluster. And you'll notice we talked about all kinds of different optimization. We talked about physical optimization on your cluster configuration settings, and optimization before you run your MapReduce job, after you run your MapReduce job, and then within it. There are really many, many places to go. How do you know where's the right place? Instrumentation, logging, and management. So it really is important as part of any enterprise implementation of MapReduce that you have a plan and a set of tools that will allow you to easily manage and monitor Hadoop. This is something that I hear all the time from an architectural perspective. It works in the development environment. I go to production and it just blows up all the time. This is particularly the case with Hadoop because the scale we're working with here is very different than the scale of relational databases. Something where you have a really small amount of data is going to be running substantially differently on a local machine than it will on a 100-node cluster. So you want to invest not only in tools, but you want to invest in load testing. It's really, really important when you're moving into production situations that you spend the time before you move a solution into production testing with production level load. And again, my big tip here is to use the cloud because it can be a lot cheaper to spin up temporary clusters with large amounts of data on the cloud, figure out what you need to tune, then come back and fix it locally before you deploy. So I've talked about MapReduce 1. MapReduce 1 is almost 10 years old. And there are several limits inherent in the API. First of all, it allows only batch processing. It wasn't really built for any sort of interactive query of data. And what that means from a practical point is you'll execute your query and you'll wait minutes or even hours. And although that's suitable for some business scenarios, more and more people want the volume of MapReduce data, but they want it at the speed of relational data, so nearly interactive. And MapReduce 1 just really wasn't built for that. As we've seen, coding MapReduce jobs is complex. There aren't enough trained developers who understand the intricacies of coding MapReduce to the level that the businesses need. MapReduce jobs don't fit all business scenarios either. You've got to remember the MapReduce algorithm was designed for one business case, which was to index the internet. And this certainly doesn't fit all the possible big data scenarios that businesses are looking to solve out there. Also, the Hadoop ecosystem is missing a lot of enterprise features for MapReduce 1. There's very little consideration for security, for high availability, and many other features that the enterprise really needs. So enter MapReduce 2, or Yarn, yet another resource negotiator. So from a high level, what MapReduce 2 does is it adds an abstraction layer between MapReduce and HDFS. And this may seem like a simplified slide, but it's really important, and it's driving the adoption of Hadoop more than anything else. Because what this allows the Hadoop ecosystem to be used for is not only the traditional batch processing or the heavy lifting or the data dump truck, if you will, but it allows for other processing to occur on top of the HDFS file system. And this is where it really gets interesting, because as the volumes of data are increasing exponentially, business wants to have the cheap storage of HDFS, but they want fast processing. So Yarn allows for a lot of interesting possibilities. There have been a plethora of new libraries coming out of the open source community that get closer and closer to interactive. And we'll be seeing that as this course continues. Things like Impala and Spark and Storm and all these libraries is funny names. But really what they do is they get closer to a more relational database like interactive processing against Hadoop volumes of data. So it's really, really exciting time in the Hadoop ecosystem. So not only does MapReduce 2 add Yarn, what it does is it adds some features that are really important to enterprise users. So what are they and how does it work? Well, it splits the existing job tracker roles into resource management and job lifecycle management. And that's important because it allows for more control and more management. Additionally, MapReduce 2 gives many benefits over existing MapReduce, such as better scalability. And it does this through distributed job lifecycle management and support for multiple Hadoop MapReduce API versions in a single cluster. As I mentioned, I think the killer benefit of MapReduce 2 is the possibility of, I put real-time processing, but I should say more interactive processing. Although with the addition of in-memory technologies, we are getting closer to real-time, which is really, really causing a lot of people to get excited about the Hadoop ecosystem. So the Yarn framework supports many different programming paradigms. So MapReduce is no longer required. In fact, we're going to look in a future movie about a library from Cloudera called Impala that doesn't generate MapReduce jobs. It just allows for a SQL-like query using in-memory capabilities in the cluster. And this fits more business scenarios. MapReduce 2 also adds more enterprise features that support security scenarios, high availability, and more. So let's drill into some detail. In MapReduce 2, you get better execution flexibility and control via map and reduce configure method, which now takes parameters. The tool and generic options parser take HCI options. And reports can use app-specific info returned from the counter info in the MapReduce methods. And what this is a lot of words, but it means control. It means better control inside of the processes. So you can instrument inside of the mapper and the reducer, gather information, and set thresholds, basically performance thresholds. There's also improvements around the distributed cache. And more with behavioral data, you're doing lookups in the mapper. So this becomes very, very important. So you can distribute read-only data for jobs. So here we are on the Cloudera virtual machine, and I've got Eclipse open, and we're going to look at the code for a MapReduce job for word count using MapReduce 2. It's a lot like MapReduce 1, but there's some subtle changes. Plus, we're going to go through the process of setting up the package and setting up coding in Java. So to do that, we're going to say File, New, Project, and we're going to say Java Project, and Next. And I'm going to say word count, and I'm going to say Finish. Now, we're going to need a class file, but before we work with that class file, we're going to need a bunch of references. So let's go ahead and get those references, and these references are to the Hadoop libraries. And we're going to get more than we actually need, and this is going to be more reflective of production coding, but this is something that you're going to want, so I'll just show you what it looks like. So we're going to go to Properties. I'm going to go to Add External Jars. I'm going to go to File System, and then I'm going to go to User. Then I'm going to go to Lib, and you'll see that I have Hadoop and many others down here. Now, we're going to start just with the core Hadoop libraries. So we're going to go to Hadoop, And then we're going to go and grab all these libraries, and we're going to say, okay. Now we're not quite done. We're going to get more libraries by doing the same thing again, going to Properties, and we're going to add external jars, and we're going to go to Client, and we're going to grab all these and say okay. And now we're ready to create our class file. So we're going to right-click on Source, and we're going to say New Class File, and we're just going to call it word count. Now again, we're not following any sort of fancy, correct programming protocol here. The idea is just to look at the code in a single file. In a production situation, you would want to have separate files for the mapper and the reducer and the runner. Now I think it's easiest to just pull the code in and take a look at it. So we're going to go ahead and do that. And we're going to replace the code that's here. And now let's save what we've got. First, let's take a look at the import statements. So we're working with some standard Java libraries. But what's interesting here is we're now working with Hadoop.MapReduce. You might remember for MapReduce 1, the libraries are MapRed. So you'll see out there in production code both MapReduce and MapRed. They wouldn't be mixed in the same file, but sometimes I do see them mixed in the same cluster. So you're going to want to take a look at that. Now, if I go down to line 13, we'll start looking at the implementation code. The first section is around the mapper, and that starts on line 15 and goes down to line 26. So you can see that we create a static class for map, which extends the mapper and takes the long writable text and text int writable out. We have a couple of variables that we use for holding the information. One is on line 16, private, final, static, writable 1. That's our initializer. That counts 1 for each word that's found. And on line 17, we have private text word new text. On line 19, we have the implementation of the map method, and that takes a long writable key text value and then has a context, which is the property bag that holds all the information. Then starting on line 20, we have the map implementation code. So we create a variable called line, which takes each line as a value and puts it to string. And then we use the string tokenizer utility class that comes with MapReduce, and we create an instance of that, and we pass the lines to it from our text input. The meat of the map method is in lines 22 through 24, the while loop. We examine the tokenizer to see whether it has more tokens, and so long as it does, we take the word object and we set the tokenizer to the next one, and then we write out to the context bag the word itself and then 1. So the output would be a key and a value, like the 1 man 1 is 1 home 1. So that would be the output of our mapper. Now if we scroll down to line 29, this is the reducer class. So similar to the map class, public static class reduce extends the reducer, takes the text int writable and a text int writable, and the implementation is on line 30. So reduce method, it takes the text key, and notice it takes an iterator. Do you remember why from when we talked about MapReduce 1? That's right, because it has to count it up. And then we have the context. On line 32, we initialize a variable of sum with 0. And then the meat of this particular method is lines 33 through 36. Again, we have a while loop. So we examine values, and we look to see when they have a next value. When they do, then we take the sum variable, and we use the Java shortcut of plus equals to signify add to that sum the next value. In line 36, we write out the results, key and new int writable sum. So the number of words, for example, the number of word the number of word man, so on and so forth. So lines 33 through 35 are performing the aggregation in the reducer. So the mapper class and the reducer class are almost identical to MapReduce 1. So you might say, well, how has this really changed? Well, if we scroll down and we take a look at the job runner class, we see some changes here. So this is our main method. The first thing is we see a new object, a configuration object. And this is the implementation of what we talked about in the previous movie, where we now have the ability to maintain configuration settings and pass them in. So you can see on line 43, we have a new job, and we're calling it word count. And we pass in those configuration settings. And the subsequent lines, we're setting the values of some of the configuration settings in code. You can also set them when the job executes. So 45 and 46 are setting the key and the value class, text and int writable, as output. Lines 48 and 49 are setting the mapper and reducer classes. And those are standard boilerplate code. Lines 51 and 52 are setting the input format and the output format classes. And you might remember that from our discussion of the methods of data input, which vary by text and some of the other standard types. Lines 54 and 55 allow for configuration around the input path and the output path in the job runner environment. Line 57 just asks the job to wait for completion and signal true to whatever environment it's being run in once the job completes. Now, that does not mean the job is successful. That just means it completes. And really, that's all there's to it. As complex as MapReduce can be, it's very, very useful to think in terms of what is the simplest possible code that I can write. Now, if you're not using the Cloudera virtual machine that has Eclipse in it, and you want to work with coding a MapReduce file in Java, then of course you're going to have some sort of Java environment. You can just download Eclipse. Another tip that I would give you is I use Eclipse Che on online browser sometimes for a zero setup. Whatever environment you use, you'll need to have a compilation environment to turn the Java code into a jar file so you can run it. Now, I did, just for convenience, put this Java file that I discussed earlier in this movie up on my GitHub. So you can just pull this file down, and then you'll have to make sure to pull in the libraries. You'll have to download the binaries from Apache in order to compile. Also, you're going to make sure that you compile to the appropriate version of Java and the appropriate version of Hadoop, which could change by the time that you work with this particular code. So you need to get your execution environment, you need to check your Java version, and you need to get your Hadoop binaries. But this is the code that I discussed earlier in this movie, so at least you can have that to start with, and I'll try to keep that updated up in my GitHub. Also, I do have an example POM file here. This is for a specific version of compilation, but it's common to compile Java using a framework such as Maven, and that requires a POM file. So just for your own convenience, I put these files up here for you to work with this code. So now that we've understood the basic coding paradigm for MapReduce 2, I want to show you some code samples on how to augment this. And I broke them apart because it can get really complicated really quick. So I'm just highlighting sections of the code to show you how to code different optimizations that we've talked about. So here I am in the mapper class. And one of the common coding patterns is to add variables for monitoring in MapReduce 2. So I've got the complete sample available also in the exercise files for this course, but I just want to call out sections here. So you can see I've added an enumerator for counters here because I want to count when I'm running this MapReduce. These are the standard variables that we've already seen, the int writable and the text. And then I have a Boolean, which is case sensitive, set to true, that I can flag to see if I'm going to skip bad records or not. So this is going to be used as a flag. And then I have a hash set here where I can store the patterns that I want to skip. And these are going to be coded usually in regular expressions. In this code snippet, I'm showing you the implementation for setting up a distributed cache. Now, you might remember a distributed cache is an optimization that allows you to ask the mapper to place specific files on every map node for the purposes of executing the map tasks. So they can be like lookup files, translation files, that kind of stuff. So here I am in the middle of the job configuration, and I'm in an if loop. And so I'm looking for, in my word count, my skip patterns. So my patterns are standard patterns. So I just want to put these files on all the mappers. So I'm going to try on the pattern files to get them from the distributed cache. And what that means is I want to get them out of the local mapper so I don't have to go to the central reducer. It's going to make the mapper run a lot more quickly. And the reason I have the skip patterns here is maybe I have some sort of spam filtering or something. So I have a master file or a master set of files on the types of things that I want to skip. So the architectural pattern here is around metadata. So you have some metadata or master data, and you want to make that available on each mapper as reference data. So the code implementation is distributed cache, get local cache files for that particular job. So continuing on with this idea of skipping files. So here we are, we have a utility method, a parse skip file method. And inside of this method, what we're doing is we're using not a regular reader, but we're using a buffered reader. So it's a holding area, if you will, so we can do some intermediate processing on our files. And we've got a while loop that basically is looking for a pattern match for the items in the buffered reader. They're reading whenever there's information in there, and then they're just looking at the patterns to skip and then adding patterns. Another architectural pattern for optimization that we talked about was counters. So here I am in the map method, and I'm working with some information in the map method. And you can see down here when I'm on the string tokenizer, I'm passing in some information to the string tokenizer, and I'm examining that information, moving to the next token. In addition to outputting the results, I've added a reporter and an incremental counter. And what I'm doing here is I'm counting the words that are passed through this while loop. The reason I'm doing this is I might want to evaluate the percentage of good versus rejected records so that I could look at the quality of the data and see if I needed to do maybe some more pre-processing or something else with the data so I can get a sense of what percentage is being rejected. Here's another pattern with a reporter. This time I'm in a reducer class. So inside of the reducer class, I've just added in the reduce parameters the reporter so that I can get information again about what is occurring based on counter values when the reducers are running. And the last pattern that I'm going to show is a job configuration with a distributed cache. You can see we've got our familiar job conf here, and we're passing in the configuration information and setting the various values. So if we move down into the for loop, we can see inside of the for loop, we've got an if construct, and the if construct is looking for -skip text. So if that equals the argument of I, then from the distributed cache, we want to add the cache file from the path coming from the URI, which can be, if you remember, HDFS or HTTP. And then from the configuration, we want to set the Boolean word count skip pattern to true. So in English, what we're looking for is if the -skip value is being passed, then we want to go ahead and check to make sure that we're matching one of the skip patterns before we skip. So it's a pretty sophisticated implementation of selective processing. Now we're going to talk about Hive. First of all, we're going to define what is Hive. Hive is a SQL-like query which generates MapReduce code. It uses the HQL language. Hive is a set of libraries which was originally developed for use at Facebook. They were using Hadoop clusters, and they had analysts who knew SQL code, who did not know Java to write MapReduce, who wanted to get information out of those clusters. So they developed this library and language. And it's used widely with all kinds of customers who are using the Hadoop ecosystem. As I mentioned, it uses HQL or HSQL. Now, this is not the same thing as ANSI-compliant SQL, which is used with relational databases, and the subtle differences in the language are really important if you decide to use Hive in a production environment. There's a lot of overlap, 60 to 70% with ANSI SQL, but not 100% compliance. Also, the underlying execution of the query is quite different when running against a Hadoop cluster generating MapReduce job or jobs versus running against a relational engine. So the performance differences are something to be aware of as well. And this is batch, not interactive. What that means is there will be latency in the results. We've seen this in earlier movies, but it's really important to understand because it's a little bit surprising if you come out of the relational world. You expect that you'll write a SQL-like query and get a pretty quick result within seconds or minutes. And depending on the size of data that you're querying, it could be minutes or even hours before you got a result of a Hive query. And it is most often used in conjunction with HBase, which you might remember from an earlier movie, is an abstraction that you create over the top of HDFS data that puts it into a wide column store with a key and then a column that contains one or more values. So again, just talking more about HBase. This is a wide column NoSQL database. And the way that you implement this using the Hive set of libraries is with a create table statement. This is very much like a DDL statement in ANSI SQL. But again, it's a subset of what we're used to out of the relational world. So when you start working with this, you're going to want to read the documentation, because if you just try to use standard ANSI SQL, you're going to be frustrated. Once your table is created, the normal process of execution is then you'll query with Hive. Some considerations around using the Hive libraries with Hadoop include the following. The Hive libraries are integrated now with HBase. It's not a requirement to use HBase, but it's most commonly done. The Hive libraries do include the HQL language. It's not a separate library. And if you choose a commercial distribution like Cloudera or Hortonworks, Those distributions include the Hive libraries. It's really only if you're trying to work from the open source Apache Hadoop distribution that you'll need to remember to download the Hive libraries if you want to include them in your implementation. Now let's understand a bit more about the mechanics of working with Hive. As mentioned in previous movies, Hive includes HQL, which is a SQL-like query which will generate MapReduce code. Specifically, it'll generate one or more MapReduce jobs. And this is actually important in understanding the overhead in the implementation of Hive queries. Hive was developed at Facebook, and Facebook still has some good documentation that they've made public around optimization of Hive queries. So if you've got a very large production implementation, that's a good source of information about Hive queries. Hive allows you to use HQL, which is highly but not totally ANSI SQL compliant. And as you become a more advanced user, it will become important for you to understand which features of the SQL language are supported and which aren't. Now, the Hive community, the binaries are open source, and there are many, many contributors, and they are working towards compatibility with ANSI SQL, and you'll see in subsequent slide here how much progress they've made. So one of the aspects of working with Hive is continuing to follow up on the releases because you'll get more functionality. It's a really active community that's making frequent contributions to the libraries. And I'll remind you again, because it's very common when you show business users Hive that it's an important part of their education to explain to them that the underlying process is batch and not interactive so that they have appropriate expectations around how quickly the query will return data. Now, because it's batch, there are some newer libraries that we'll be looking at in subsequent movies that actually make use of the memory of the machines of the Hadoop cluster that can return the information more quickly. So sometimes you'll want to use a Hive query, and sometimes you'll want to use some of these newer libraries. They include libraries like Impala for Cloudera, for example, which make use of memory to get a quicker return on a SQL-like query. And we'll see this when we work with the Hue interface later in this movie. It's really important to understand which library you're using so that people who are actually writing the queries have appropriate expectations. Hive is most often used in conjunction with HBase. Another way to think of HBase is to define a schema on read, because very often the source for the HBase tables is your HDFS file system, and you create tables out of there. So I'm going to show you what that looks like next. So very frequently you use the create table statement and you just define the columns. This is just a simplified version. And then you run a select from that table against it. So it really provides a nice level of abstraction that makes the data in your Hadoop cluster much more accessible and usable to a broader number of people because, of course, the ANSI SQL language has been around for many, many years, 10, 20 years. And so there's a big base of people that understand that as compared to the amount of people who are able to write a more lower level MapReduce process in Java. So this is a pretty good summary of the state of Hive as of this recording. So you can see that we have Hive versions by color. We have light green, dark green, and blue. And we can see that we have the compatibility of first the Hive SQL data types on the left side. You can see that the main data types are all compatible. The newest one is the compatibility of decimal. You can see that data types that we're used to in the relational world, like date, aren't yet supported. So again, you have to do a little bit more work in a Hive query to have time awareness, if you will. And then over on the right, we have some specifics about Hive SQL semantics. So you can see that the most common ANSI SQL statements, such as group by, order by, the left, right, and full on outer join are supported. However, I will caution you that the join implementation is very different on a Hadoop cluster than it is in a relational database and can have substantial performance overhead. So even though you can perform it, you want to really test that with subsets of your data before you release that out into the wild. See that in this particular implementation, the ANSI SQL statements that are around intersect, except, union, distinct are not yet supported. Subqueries and halving are not yet supported. So there's some common ANSI SQL that's not yet supported. And again, if you're going to be implementing Hive in a substantial way in your production environment, you're going to want to really dive down and make sure that you understand the differences between your base of knowledge, which is ANSI SQL, and what's supported in the particular implementation of HQL that you're working with. So more on the mechanics of working with Hive. you have to make sure that the Hive service is actually started on your particular cluster. Again, when you use the commercial distributions like Cloudera, it'll be turned on by default. There's another aspect of working with Hive that's in the newer versions. It's around this concept called the metastore. So the metastore stores the metadata for Hive tables in a database, and that database can be embedded, local, or remote. And there's a lot of guidance about how to set up the metastore that's particular to the specific vendor distributions. So again, if you're going to be working with Hive, you're going to want to make sure and set up the metadata in the most optimal way for your particular situation. When you're testing, you can just use the embedded, I think it's a Darby database for Cloudera, for example, small and lightweight. But when you go into production, you really want to have a consideration of where you want to put this so that it's most accessible. And in some cases, you want to have it highly available. There's an enhancement to the most current edition of Hive called the schema tool, and it allows you to work offline in terms of schema manipulation for your metastore database, which is a feature that a lot of customers wanted. So I just wanted to call that out here. And again, this table compares working with, for example, MySQL, which of course is a relational database, and it compares it with HQL. And you can see it's basically the same in terms of working with the metadata. But again, any of these ecosystems are works in progress. So this is current as of this recording. You want to always verify for your particular vendor, for your particular version, how you access the metadata, which SQL-like statements and in what format are going to work for you. It's just really best to look up the documentation. This is just based on my practical experience of having a deep background in ANSI SQL, and if you just kind of guess, you'll end up being frustrated. It's better to just look up what are the limits and then kind of go from there. As we've been looking at the particulars of Hive, we should really discuss who and why you might use it as opposed to some other method of getting information about your data from your Hadoop cluster. The number one reason I see people using Hive is they have a background in ANSI SQL. Most commonly, the community that enjoys Hive and finds it to be very useful and productive is the analyst community. They are generally very advanced ANSI SQL users and often also are using Excel very frequently. What they are not is they are generally not object-oriented programmers. Object-oriented programmers usually prefer to use a more low-level MapReduce kind of an algorithm with Java or some other OOP language. Again, if you know ANSI SQL, HQL is going to feel familiar. Just heed my caution from practical experience, which is to research the differences before you start running HQL queries on your cluster. Hive is useful for asking analytical style questions, questions you would ask with ANSI SQL. So selecting information, sorting information, doing basic aggregations for information, so summing, averaging, min, max, those kinds of questions. It's not as useful for data cleansing. So what does data cleansing mean? Data cleansing means parsing, formatting, processing, stripping out white space, those kinds of processes. They can be done, but as you'll see in the upcoming example, it's a little bit cumbersome because that wasn't really the purpose of the SQL ANSI language originally. For that, you'd probably rather use either the lower level languages, so MapReduce, or what I'll be showing in subsequent movies, a different abstraction language, Pig, which was developed at Yahoo just for that kind of work, which is also called ETL, or extract, transform, and load work. And again, I know I've said this over and over, but I've seen this so often, this confusion. It's really an important part of the education around the use of Hive. Hive gives you the convenience of a SQL-like language, but it does produce MapReduce batch jobs. So if you're wanting or needing to have a more interactive type SQL access to your HDFS data, then Hive is not the particular library that you want to use. I generally will use Impala for Cloudera, and there are some other newer ones that we'll be talking about near the end of this course. Another reminder when working with Hive out of practical experience is, although you can do joins, the kind of joins that we're used to in the relational database world, so an inner join, an outer join, left-right join, so on and so forth, Hive is producing MapReduce jobs, and the overhead that can be caused by joining these tables that are only lightly related, because remember, HDFS data or even HBase tables have no need to be normalized or have formal relationships between the data in the tables. So what that means practically is if you're trying to force a relation from one table to another, most commonly all the data in all the tables has to be scanned or read, possibly more than one time. So joins can be very, very resource intensive in a Hadoop environment. So you're going to want to test them and also really evaluate the execution of those types of processes in production level loads. So when we are working to understand the different libraries, we use word count. And so we're going to take a look at word count, which we saw in previous movies implemented with MapReduce, implemented via Hive. We're going to start with pseudocode. The process would start by you creating an HBase table for your text input, and then you would load your data into that table, and you could load it from HDFS, or you could load it from some other source, your file system, or if you're on the cloud, S3 or something. And then with your Hive statement, you would create a new destination table, and that table would be loaded with the processed results. So the processed results would be processed via a nested select statement, which I'll show you in the next slide here. So this is a partial example. This is kind of the center of that example. So you create the table, and you create it with two columns, word and count. And then you're going to create it from select explode, split, lowercase, regular expression replace, regex, for the line, and the punct and the control split the words. And you can see they're splitting on spaces here, so it's not a very sophisticated regular expression. You would probably have some errors, and you'd have to write a longer regular expression. And this really is kind of the guts of this, the regular expression, which they always say regular expressions are easy to write and not easy to read, which does cause them to be not as usable as some other mechanisms for processing. And you split as word from my input. My input would be the original table. And then you're going to group it by word, and that's going to give you your aggregate, because you're going to add up the number of occurrences of a particular word. And then you're going to order it by count. So put the count of the words in order, descending, and the word ascending. So the tricky part of this, I think, is the regex, and it really kind of shows that Hive is not necessarily the right language to use for this kind of a problem. This is a parsing problem that we're doing here. And as we covered in earlier movies, this is done with OOP code in a more sort of natural way. And as we'll see in subsequent movies, it can be done with a higher level language, again, in a more natural way with the pig language. So even though I showed word count, I generally wouldn't use Hive to execute a word count. If that was the only language I knew, possibly. Rather, I would use Hive to retrieve the results out of an HBase table and possibly do some aggregation on it. So some counting, averaging, min, max, that kind of thing. Now, there certainly can be more complex Hive queries, and it really depends on your particular business situation. But I really like to use the best library, the library that was designed for the appropriate type of business task. There are some other considerations when using Hive, so let's look at them here. Of course, we're going to look both at the HBase tables and the Hive queries when we're looking at our implementation. There are a number of ways that you can consider query optimization for Hive. The reason I included the HBase tables is there's a whole lot of documentation and information about using subsets. There's another set of query optimization techniques around CBO, or cost-based optimization. Now, in order to understand cost-based optimization, you have to understand the execution methods and processes and where the bottlenecks are when you're executing a Hive query. Another group of query optimizations is around using column-based statistics, and this is somewhat analogous to relational indexing, but again, it's not the same thing. I wanted to show you an example of a Hive query plan. There is a command, and you can see it here at the top of the screen, explain, that you can run before a Hive query, which will give you a text-based output of how that particular query has been run on that particular Hadoop cluster. The way you read this is from bottom to top, so that you can see it starts first with 00, which is scanning the HDFS system for the customer address table. And you can see there's one partition here, but most commonly in production you'd have multiple partitions, and it shows you the size. And step 1 is to perform the aggregate. So the aggregate is counting for each partition. So this is analogous to the map function. If you had more partitions, you would have more instances of this first aggregate. Step 2 is the exchange. And this is showing you the shuffle and sort phase of the MapReduce job. And you can see that this is unpartitioned because we have only one partition. Step 3 is the reduce phase, the merge finalize. So what we're doing here is we're taking the output from each of the individual aggregates or the mappers, and then we are reducing them or we're merging them to one final total count. So this is a very, very simple example just to get us started because, again, the query plans and the process look deceptively similar to relational query plans, but really they bear a little resemblance because the underlying processes are MapReduce, even though we have a relational-like statement on select count star from customer address up at the top. Next, we want to look at Hive by example. In order to do this, we can look at one of the distributions, and we're going to look at Cloudera. Cloudera includes a Hue tool, which is a graphical browser, which makes it really easy for us to just spin up and check out some of their sample Hive queries. In order to run these samples, you have to install them on your developer cluster, and I'll show you how to do that in the demo coming up next. In this section, we're going to take a look at running some Hive scripts. Now, I've put course files up on GitHub because Hadoop ecosystem is evolving, and for the most current course files, you're going to want to take a look here. So we're working with Hive or HBase, and so here we are. And we'll be creating a table, and then we'll be querying a table with HQL. So I'm just going to open this up. You can just pull down this repository, or you can just copy and paste this code into your execution environment. Do notice that we have semicolons at the end here. So this is a create table statement, and then we're just inserting some values into the table. Now, as I mentioned in an earlier movie, there's a number of ways you could execute this depending on your dev environment. You could be working with a local Hadoop cluster. You could be working with this Hue shared environment here. You could be working with a GCP Dataproc cluster. Now, if you are working with this shared environment, do be aware that you will get timeouts and warnings because it is shared. And one of the things that's nice in working with it is you can kind of see what other people do. So you can see query history, you can see, information about working with Hive, example tables, so on and so forth. It truly is a playground, but it really is just for experimental use. Personally, I like to set up a Dataproc cluster because then it's dedicated to me and I can spin it up and spin it down really fast. So I've done that here. So I've got my cluster set up. And again, if you shut off your cluster and recreate it, you can use a GCP script, which you can generate when you create the cluster. So at the bottom, I'll just show you how to do this again. You can just say a command line, and that would give you a G-Cloud script of whatever your configuration is. So what I've done, again, just to make things kind of easier when you're setting up and tearing down, if you happen to use that metaphor for setting up, I just pulled a generic script here. And you would have to replace some of the values for your particular project. For example, on line 20 here, you'd put your project name, and this should all be in one line. I don't have the continuation characters. So you would just run this in a Cloud Shell, and then you could just quickly set up your cluster rather than clicking through each time. You just copy and paste this into, it's a virtual machine that's a client on your account, and then it would create your cluster. But I already created the cluster. And I've actually already run some jobs. So I'll show you the process of running these jobs. So inside of my cluster, if I wanted to submit a job through the UI here, I would just give it the job name. So I'll call it Hive job. And then I would select the region, select the cluster. And then in this case, we're working with Hive. So we have two different ways to do this. We can use the query file, which would be an HQL, or we can use query text. So you can literally copy and paste query text right in here, which would be like going through here and going back here to Hive and copying this. Now, remember that HDFS file system is immutable, and so you can only run this one time because after this, the table will have been created. So then you would paste this in here and you would just click submit. Now I've already done this for the purposes of time, and you can see if I go over to the jobs that I created this Hive person table. It took 26 seconds. And if we go into this, we can see that the job output is complete. And there is the configuration. Of course, we wanted to run it again. We could clone it, but we'd have to create a table with a different name. Now, if we wanted to query the information inside of here, what we could then do is we could just use, and I wrote an example query against this data, select the last name, first name from this table where the city is Bergen and put it in order by last name. And again, the process to submit this is just the same. We would just submit the job. We would paste the query text in. And here I've run that. It took 27 seconds. And you can see here's the output. It gives us the transaction isolation level as well. And then here's the job configuration. So what I really like about the Dataproc environment is it's a quick setup, quick teardown. You know, I'm spending my time working with, in this case, Hive and HQL rather than setup and drivers and everything else. So I really recommend it in terms of studying. Of course, as I've been saying, there is a cost to this cluster. And so what you're going to want to do is get yourself in the habit of when you're done, you're going to want to delete it, which might seem a little odd, but it is kind of the cloud native metaphor, which is to have what they call ephemeral, in this case, server clusters. They're not long lasting. You just spin them up, do your work, and spin them down. And in addition to having a great environment for learning Hadoop, you're really starting to work in a more cloud native way as well. The next library that we're going to take a look at for Hadoop is called Pig. Pig is an ETL library for Hadoop, and it generates MapReduce jobs just like Hive does. It's a higher level abstraction, and it was developed at Yahoo. Now, ETL is a different kind of process than a generic query process, and we're going to be talking about that in this section quite extensively. ETL stands for extract, transform, and load. The Pig library uses the Pig Latin language, so these people at Yahoo had a sense of humor, and it uses commands like oink and grunt, really. So let's smile and start working with Pig and Pig Latin. So when should you use Pig versus Hive or MapReduce? When you have processes that are ETL-like. If you come out of the relational world, you might have used ETL tools for SQL Server, for example, such as SSIS, SQL Server Integration Services, which allow you to create ETL data transformation workflows. Other implementations of these kind of tools in the relational world are things like Informatica, and Oracle has a set of ETL tools. So the idea is when you have ETL-like jobs or tasks, you want to use Pig as an abstraction language because it was specifically written to make those kinds of processes easier. So examples are transform data. For example, you might have a set of text data coming in, a big blob of text, and you might want to split it into words. So our sort of classic word count. You'll see, I think, in our example, that the implementation of word count is actually more elegant and simpler using Pig than using Hive. To clean data, it's really common in big data scenarios that you're bringing in behavioral data and it might have junk or data that is incorrect, improper, or that you don't care about. For example, you might be collecting data from sensors and maybe there was a blip or an outage or there's some incorrect data. So you want to look for data that is incomplete and then you want to discard it. To process data. In big data scenarios, the volumes of data can be exponentially more than you're used to dealing with. So using the Pig language against HDFS and Hadoop platform really makes a lot of sense when you've got a tremendous volume of data and maybe you just want to aggregate it up. An example might be you might get location data from all of your customers worldwide as they go through your stores or go through a certain section of the offering that you have. And maybe you only want the data from a certain time period, from time A to time B, and the rest of the data you don't need. So it's a great use of resources to dump all that data into a Hadoop cluster and then use Pig to filter and process that data. So how does Pig work? Generally, there is an ETL process and flow that looks something like this, and the all capitalized words are keywords in the Pig Latin language. So you're going to load some file or files, and again, just like with Hive, you can load from a file system, a standard file system, a cloud-based file system, or you can load from HDFS. And then you're going to perform some operations. And you're going to find, as you work with Pig, that there's a rich set of functions that are associated with the Pig Latin language. So functions that you're used to and you're going to find very useful, like filter, join, group by, for each. I want to call your attention to the generate function because this is really commonly used in ETL Pig workflows. Generate allows you to do some process on the intermediate data and then to generate some new values. So it's a really common programming paradigm in Pig ETL process flows. And then you'll usually take the output and either dump it to the screen for testing so you can look at it and see if your process is correct, or if you're satisfied with it, you'll store it to a new file location. And as with other processes on Hadoop, you can choose to store your output as new files into the HDFS file system, or you can store it into some other file system which can be local or cloud-based. Another consideration if you're working with HDFS is to remember that HDFS files are immutable. So if you are transforming and you're creating new results or really making any change whatsoever, you're going to have to create new HDFS files. So sometimes as part of the process, you'll move or put the old HDFS information back into a less redundant file storage. That can be part of a workflow. For example, on Amazon, sometimes I'll move the original HDFS back into S3 because the storage is cheaper. You might remember that HDFS by default is triple redundant. And so if you already processed those files, it's a real common workload that you don't need to keep those in HDFS anymore, the original files. Maybe the results will stay in there, or maybe they'll go back, in my case, into S3 as well. As we're learning more about Pig and Pig Latin, we're going to cover a couple of core concepts so that you can make quick use of this framework. The first set of concepts is around how Pig represents data, and it's pretty simple. So it has fields, which is a single piece of data, a tuple, which is a set of fields, like a key and a value, for example, and a bag, which is a collection of tuples. So multiple sets of keys and values. And you can see how this aligns nicely with the MapReduce paradigm because, as you'll remember from the sections on MapReduce, the output from the mappers and the reducers is a single tuple and then a set of tuples, which is a bag. Pig also has the concept of a relation, which is a complete database. It's just a little bit different than the idea of a relation in the relational database world. That obviously is the relation between the data in tables. So in the Pig world, a relation is a complete database. So I wanted to call it out here. Another important concept in the Pig world, because I really think of it as a dump truck for processing data, is to filter. So I wanted to take a minute to talk about filtering. It's a really, really common methodology in working with Pig scripts. So the syntax of filtering is you filter some set by some value. So it's like a where clause, but it's just out of the relational world, but you use the word filter. It's really very similar, and for those of us that come from the relational world, it's simple and natural to use. It supports all of the operators that we're used to in terms of the logical operators. They work the same way, as well as the relational operators. So I just called them out here. It just helps you get very productive very quickly with the Pig language to understand that there's very good compatibility with ANSI SQL here. Another aspect of the Pig language is a very rich function library. Now, when I was talking about Hive earlier, I cautioned you to look at which aspects of HQL were supported as it relates to the superset of ANSI SQL. In Pig, what I find is Pig actually has more functions than what you find in ANSI SQL. So it's kind of the other way. They have pretty much everything I've seen there plus more. So I called some of them out here. And again, depending on the type of data manipulation, the type of ETL processes you're doing, you're going to want to dig into these function libraries. Rather than killing yourself trying to write something manually, you might be surprised that the function already exists. So I put the top level categories here just so you can get an understanding of what function libraries are available. So there's the general or standard, and you have average, min, max. I did call out tokenize. Tokenize is a function that I'm going to show you in a demo coming up. And what it does is it splits words. So it splits text into words. It's a really useful function when you're analyzing string-based or text data. And it's much simpler, I think, than the Hive implementation I showed you in an earlier movie. So these functions are available and really commonly used. There's a set of relational functions. I showed you filter. I also want to call out that because this is a superset, there are functions like MapReduce, where you can actually call a MapReduce job from within a Pig script. It's kind of interesting because you might think it would go the other way, that you'd call a pig job from within MapReduce, but nope. You have a pig script, and then you have a MapReduce job, usually written in Python or Java, that you can call, which is sort of like a super powerful aspect of a pig script. So again, it's a different way of thinking about an ETL process, kind of stringing these things together, but very, very commonly done in production situations when you're processing these huge amounts of behavioral data and getting them down to something useful. You, of course, have also string functions that you'd expect, things like uppercase, lowercase, substring. That's pretty standard stuff. You have your math functions, absolute value, logarithmic functions, rounding. And then you have a unique set of functions around loading and storage. I called out here the JSON loader because there's more and more JSON data coming from the web. There's also some functions around compression that can really make your pig workflows run more quickly. So again, I really advise as a tip, if you're working with production level ETL pig scripts, that you take the time to investigate the function library. If in pig, the functions that are presented are either not sufficient or not performant, pig also includes the idea that you can write your own functions. Now, this is a very advanced topic. However, I have used this functionality in working with production customers, so I wanted to mention it here. The idea is that if you do not get adequate performance out of a pig-defined function, you can write your own. So if you're doing that, you're going to need to write the function, register the function. I highly recommend you test the function under load, and the functions can be written in Java or Python, and then they can be combined as part of your pig workflow. There are several different ways to run a pig script. Let's go over them here. The first way is in script or batch mode. You just run your script from the Hadoop shell. The second way is, and this is just goofy, but in grunt or interactive mode. From the Hadoop shell, you type the word pig, which will start the pig shell. And the third way is the embedded mode, and that's within Java. Now you might be wondering, why do we have these ways? When do you use them? Script or grunt are used during the testing phase, and the embedded mode is very often used in production because it's very common that you combine scripts, you chain them together in a process that is repeatable and quite complex when you're doing processing of real-world data. Let's take a look at word count, our hello world for the Hadoop ecosystem, using pig. So I'm going to just go through this simplified example so that we can compare and contrast this to word count in some of the other languages and libraries. So first, we're using the concept of aliases. So we have variables, so lines, words, grouped, word count. Those are aliases. And then we're setting them equal to values that are generated by pig. So lines is equal to calling the load keyword. We're just loading some text. And then we're loading it as a character array, which is a data type in pig. And we need to load that type to be able to use with the function so that we can process it. To the words variable, we're using the for each keyword against the lines input. And then we're calling several functions. So this, I think, is really quite elegant. And I want to contrast this with what I showed earlier in the Hive, where we used a regex, which to me was kind of unreadable. So we're going to generate a new output. We're going to flatten or group that output, put it in a bag, and then we're going to tokenize, which I think is kind of beautiful. I'm a little bit of a nerd, but we're tokenizing the line, which is doing a basic split of the text into words. Now, the tokenized function separates on spaces, and that might not be sophisticated enough for your particular implementation, so you might have to write your own tokenize, but for a lot of implementations of basic text processing, it's good enough. And then you get a word, and then we have the grouped variable, which is going to group the words by word. And then for the word count, for each grouped, we're going to generate a group, and we're going to count the words, and then we're going to dump out the results. Now, are you starting to see the patterns? Are you starting to be able to see where the map would occur and where the reduce would occur? For me, it's easier to think backwards. If I look at the word count variable, it's clear to me that's where the aggregate is going to be generated. So we're going to have these key value lists that are generated, and we're going to group them together. So that's going to be the reducer. So the words variable and the grouped variable are where the mappers are going to be generated. Again, it's really critical as you're working with Hadoop data that you think in terms of MapReduce. That's why we took the time in the earlier modules to go down to that low level and write the MapReduce code. Even though you may not use it in production, you may use Pig or you may use Hive. More and more customers do because they're simpler and more flexible. However, when you get into real production situations, you need to be able to translate back down to mappers and reducers so you can find out where bottlenecks occur and debug and fix them. Now we're going to take a look at Pig by example. We're going to again use the Cloudera distribution on the virtual machine, the Hue tool, and we're going to look at the Pig samples. So in the next section, we're going to take a look at running a Pig Latin script on a Hadoop cluster. Again, I put exercise files up in my GitHub repo, companion to this course. So if you go to the Use Pig section, and this talks a little bit about the Pig Latin library, how to work with the shell. And I have some sample data here. This is basically the text of Shakespeare. I have it in 2 different places, actually. And then I have our script, which is we're going to run word count. So it's 5 lines in Pig Latin to run word count. So let me go through these lines, and then we'll see what this looks like when we run it on our cluster. So in line 1, we set the lines variable equal to the contents of the Shakespeare.raw file, which is just the text, which is being stored in a Google Cloud Storage bucket called Hadoop course. And we store that as a line character array. We set the words variable via a for each command on the lines. We're going to generate, we're going to flatten, and we're going to tokenize the lines as word. So what happens in Pig is there are a lot of operators that replace the need to write certain regexes and certain pattern matching because the language was designed, as mentioned in earlier movies, to help to manipulate data, or ETL, as it's called, extract, transform, and load, or ELT, extract, load, and transform. Then we're going to set the grouped variable to group the words by word and set the word count using the for each on the grouped variable. We're going to generate a group, and then we're going to use the count keyword to count the words, so keys and words. And then we're going to dump or output the word count. So again, you can just copy this. Now, a couple of setup points here. We're working with a data lake pattern rather than HDFS. In line 1 here, we're accessing our source data from a bucket rather than the HDFS file system. You could just change that if you're working with local HDFS cluster to an HDFS command to access that. And then, of course, you have to put the data in the bucket. So your bucket name will change and your bucket contents might look different. But here's the Shakespeare raw. And then what I've done, just for simplicity, is I edited the permissions and added all users read, which makes it public. And then this gives us the URL for the particular string. Again, it's like cooking show. I've gone ahead and implemented this, even though it only took 41 seconds, just a little bit faster for showing you guys. But if you wanted to set this up, you'd click Submit Job, give it a name, and then select your region, your cluster, select Pig. And as we did in an earlier movie with Hive, we could use a query file or query text, and we would just literally paste this query text in. Notice again, we have to have semicolons. So we would paste this in here, and then we would just submit the job. So once we do that, this shows the result. So here is our job. It succeeded. And we can see here's our word pairs, basically. So if we scroll up, you can see some of the words like conjure occurs 4 times in this particular Shakespeare text. And you can see how long it took. And here is our configuration. So again, I know I'm emphasizing this, but I think it's really important because I see a lot of people struggle with Hadoop setup. And I really like using the cloud for running these different types of libraries, long as the libraries are available. Now, in the Google Cloud Platform implementation, you do have a certain set of libraries. There's a different set in AWS. For example, they have some libraries that aren't available. And I'm not saying you can't SSH into the cluster and install your own libraries. I just find that when you're learning, it's just nice if you can have the environment set up. And again, just to remind you, when you are submitting jobs, the job types that you have here are Hadoop, Spark, Spark-R, PySpark, Hive, Spark SQL, Pig, and Presto. And this is based on the way that we chose to set up our cluster configuration. Also, do remember when you're done testing to shut down your cluster so that you don't get surprise charges. So just go over here and delete your cluster and then recreate when you want to explore your next set of scripts. And now we're going to learn a little bit about libraries in Hadoop that have to do with workflows and data connections. And the first one we're going to take a look at is something called Oozie. They all have these funny names, but we're going to explore them in a little bit of detail here. So Oozie is a workflow scheduler library that's used to schedule one or more Hadoop jobs on a regular basis. You can use it one time, but it's most often used in production environments to schedule reoccurring jobs. So it's kind of like the SQL Server agent, but a little bit more sophisticated in that you can glue together or combine different types of jobs. So in some ways, it's more like SQL Server integration services or Informatica or an Oracle ETL tool. What kind of jobs are often scheduled with Oozie? Well, really, there's a large number of them, and we haven't covered all of the Hadoop libraries at this point in the course. So I thought I would just show some of the libraries that we have covered being scheduled by Oozie. Now, this is kind of an academic exercise because you would normally just run the individual HQL script or the pig script, but it kind of will give you the sense of what Oozie is capable of without getting into so much complexity. As I mentioned, you can schedule based on time or other factors such as changes in the data. And this is most commonly scheduled around new data arrival into an HDFS cluster. So native Oozie is written with a command line, and it's written around jobs and bundles, which are groups of jobs. It has a syntax as you would expect, starting with the word Oozie, and then you have various options that you can do: start, stop, suspend, resume, info, so on and so forth. You'll see when we get into the interface that the jobs are referred to by the job number. So I'll point this out. This is something I haven't mentioned to date in this course, and it is kind of important when we start to schedule jobs. Now, most people use some kind of a tool to work with Oozie because the core syntax is XML, and most of us do not want to write job scheduling in XML. So for the purposes of showing you, I'm going to again use the Cloudera Hue browser, which is a pretty simplified version of what can be done with Oozie, but it is a lot better than writing XML. So before we take a look at the Hue browser, I'm going to just make a couple points from my production experience about optimizing Oozie workflows. When you pick up a vendor distribution for Hadoop, which you usually will use in production, you want to look at that vendor's implementation of Oozie if you're going to use it. For example, if you use Hortonworks, one of the things that they advertise is that they have a better scheduler, so an improved scheduler than what Oozie offers. And that can sometimes be important in your particular situation. So this can be one of your decision vectors when you're trying to figure out which vendor to use or which tool. Another thing you can do is you could actually use an alternative product. Now, most of those alternative products do cost money, so they're going to add cost. But some of the customers that I've worked with prefer to use a tool that they find to be in a more complete state, particularly in the graphical user interface implementation. And some of the ones that I've worked with are Luigi or Azkaban. Here we are back inside of the Cloudera virtual machine, and we're using the Hue browser. We're going to take a look at various workflow libraries, and the first one is going to be Oozie. Now, if we click on the workflow button, we'll see that we have dashboards and editors. So it's a little bit confusing because it doesn't say the word Oozie here, but actually this is going to give us access to it. So let's actually just navigate through this so you can see what we're looking at. Also, do note they have a link to native Oozie up at the top, but we really don't want to go out to this website. We want to actually work inside of Oozie on our cluster. So again, it's a bit confusing. So we're going to go to dashboards and workflows. And inside of here, you can see that I've had several unsuccessful jobs, and I just ran some jobs so you could kind of see what this would look like. So I had some jobs that are related to data transfer and a job that's related to Pig, and that one succeeded. And you can see that each job instance has an ID, it has a duration, and I can click into the job, and I can see information about the job, and I can look at any of the variables configured with it, any of the tasks, actions, details, log. So again, this is really for enterprise data movement. So I'm going to go across the top. I'll also mention here I have workflow, I have coordinators, bundles, which are groups of jobs, SLA, which is service level agreement, or I have actually the information about the Oozie service itself. And Oozie is installed by default in the Cloudera distribution. Again, if you use the open source Apache distribution, you would have to install the Oozie library and configure it, which is a complexity. And you wouldn't get this browser. You'd have to write Oozie jobs in XML. So let me go over here to query editors, and you'll see I do have a job designer, but again, I don't have Oozie. If I go to data browsers, I don't have it. If I go over to workflows, I can look at my workflows here. If I want to make a change, I have to go into editors. So I'm going to go into editors and workflows. And you can see here in the workflow manager, Cloudera has provided us with several examples. So if we scroll down, let's find an example of some type of action that will make sense for us. So I ran the pig action earlier. I'm going to go ahead and go into the Hive action right now. So I'm going to go into the Hive action, and I'm going to actually open that up. And what you see here is a graphical interface, and it's a little bit tricky to see. So here's the start or the pre-run activities, and these are the activities that you could drag on. You know, if you come from the Microsoft ecosystem, it's kind of like SQL Server Integration Services where you drag an item on. And here we have one task, we have a Hive task, and here we have the end of the script. Now, inside of here, if I click the edit, you can see that this is Hive, and I say demo. And then I scroll down, and it's going to run a SQL script. If I want to see that script, I just click over here. And then you can see it's on my HDFS file system. And I could actually upload a new script if I wanted to. So it's just a wrapper, really, around this particular script. So now if I say done, it's going to say that I can't save this. And the reason I can't save it is these samples are read-only. So what I need to do if I want to try this out is I need to make a copy. So let me copy it. And now I can see that I have a copy. And now if I want to go in here and make a change to the property, just to give you a sense of what this looks like. And then I'm going to say done. And now I could either immediately run this job by clicking submit, and it's called a workflow, or I could schedule it, or I could export it. Do you remember what format it would be in if I exported it? That's right, it's XML. So let me go ahead and submit this job. And it reminds me I need to save it and submit. Now, do you remember from the Hive sections of the course what kind of job flow this will actually create? If you said MapReduce, you were right. You might remember that Hive and HQL actually creates one or more MapReduce flows. So you can see this job is running, and you can see up in the job browser over here, we could actually look at the status. Now, you might remember from the Hive module that Hive jobs are designed to be more lightweight than, say, pig jobs. And we did get an error, and our error is because we were unable to instantiate our metastore. Again, from the Hive section of the course, do you remember the role of the metastore with Hive queries? If not, I'll remind you, the metastore keeps the information about the HBase tables. A lot of dependencies, a lot of terms. So now I'm going to go back to the editor, to workflows, and you can see here's my Hive copy. And if I wanted to rerun this job, I could just click right here and I could submit it. Now, if it didn't work, I might just want to move it out to the trash and work on a new job. There's lots of different types of jobs that you can work on inside of the Workflow Manager. And as we progress through this section of the course, we're going to increase in complexity because, like I said, it's not normal to use Uzi to run a single Hive script. Normally, you would combine Hive, Pig, other types of libraries to have a complex workflow against your data. As we're continuing our tour of utility libraries for Hadoop, the next one up is called Scoop. Scoop for Hadoop. These names are kind of crazy, aren't they? So what's Scoop? Scoop is a command line utility for transferring data between relational database systems and Hadoop. You can use it to import data from those systems into Hadoop or to export data from Hadoop back out into those systems. You can also load that data not only into the HDFS file system, you can load it directly into Hive or HBase tables. Scoop contains connectors for Oracle and SQL Server and other relational databases. Let's familiarize ourselves with Scoop syntax because it is a batch language, so you generally will write out the Scoop commands, and they're not very verbose. They're pretty intuitive. So if you're going to do an import, for example, you just say Scoop import, and then you set the various parameters. Now, an interesting aspect of Scoop is that in Scoop 2.0, which is the latest version as of this recording, the separate RDBMS connectors, there is one for Oracle and for SQL Server in Scoop 1.0. Those have actually been dropped, and in Scoop 2.0, you use a JDBC connector for all relational databases. It's really interesting. This is one implementation of a Hadoop library where some people are choosing to stay on the older version because they prefer to use the database-specific connectors. So you're going to want to test that for your implementation based on the type of database you're importing from and the volume of data to see which connector is most performant for you. Then you're going to specify the table name, username, password, and optionally the Hive import flag. Now, to optimize Scoop, in addition to using either the JDBC or earlier database connectors, there is an option to do something called direct dump. And in my working with clients, sometimes the direct dump meets their needs and it works faster than the native database driver. Other possible optimizations for Scoop is to monitor the number of parallel connections. You could also use a third-party product if the performance of Scoop was not adequate for your situation. Now, those usually cost money as opposed to Scoop, which is free. And then, as I mentioned earlier, Scoop 1, as of this recording, actually has more features, particularly around drivers, than Scoop 2. I'm sure that will change in the future. But again, this just underscores when you're using any sort of libraries for Hadoop, you really want to research as to which features are important to you and which features are mature and included in that particular version of the library. Here we are back in the Cloudera Hadoop virtual machine looking at the Hue browser to look to see some Scoop examples. So we're back at the homepage and you can see here is a Scoop action. But before we go there, let me just help you ground some of these various libraries in what they do. So we've been talking about queries in previous movies and query libraries, so Hive and Pig. We just talked about workflows with Oozie. And now we're talking about moving data around. So notice that Scoop transfer is made available here under data browsers. So I'm actually going to go down here to the Scoop action and open it up. And do you note that the Scoop action opens up in the Oozie editor? Now again, this is a little bit of overkill. It's just a sample. You could run an individual script to run your Scoop import. But it is common in production to wrap your Scoop action, your Scoop script, in a workflow so that you can have scheduling about it. So if I scroll down, here's my Scoop action, and you might remember from the last movie that in order to make changes, I'm going to have to copy this because this is read-only. So here I have a copy, and I'm going to open this up. Here's my Scoop demo, and I'll call it Demo 2. And then I'm going to look at the command. Again, it's very simple. Scoop, import, connect, JDBC. I'm actually not sure if this file exists, so this may or may not work, but that's okay. And create a table and into the target directory set by the output variable. Another important thing to remember when you're doing any sort of data movement in Hadoop is that the HDFS file system is immutable. So you're going to have to set some variable if you're going to do this on a repeated fashion, because the first time it'll work, but in subsequent runs, you have to have an update to the name of the directory or it will fail because you cannot do any sort of update to Hadoop files. It's only create or delete. There is no update. So I'm going to go ahead and say done, and then I'm going to go ahead and say submit and save and submit. And notice I have to put the output. And if I remember correctly, this output doesn't resolve, but we'll see how it works. You can kind of see how it looks like. There it's running. And again, we have our job browser so we could monitor the progress. It's really common in production that you're going to have this distributed across parallel workflows in order to optimize it. And notice, are you noticing the subtleties of the Oozie dashboard? We have the start OK because there was nothing in there. This would be the configuration scripts. And again, we got an error, so we can go ahead and we can look at our error, and I believe it's because the port out of range. What I believe it is the path is incorrect when I looked at it. Here's our logs. And so it's telling us on our standard out that the destination was not available, so our path is incorrect. This is a common error when you're configuring because you're configuring data sources and destinations into the Hadoop file system, which you really have two possibilities for getting it wrong. One is you actually don't have the correct path. Two is you have the correct path and the folder already exists. That may seem like a silly error, but in working with Hadoop with customers, I find that happening really, really often because it's a different method of working with the file system. The operating system file system, of course, you can update, and the HDFS file system is immutable. So once you create that folder, you can't create it again. You have to create a new one. We've got yet another workflow library to talk about, and that's called Zookeeper. And if you guessed, it's for all the animals in the zoo, like the pig and all those other animals, you'd be right. I don't know who makes up all these Apache names, but they do have kind of a weird sense of humor. So what is Zookeeper? It's a centralized service for Hadoop configuration information. Well, that's a lot of words, but what does that mean? What do you use it for? It allows for distributed applications. It creates an ensemble of applications. So again, it's used as a coordination service for large enterprise Hadoop projects. Zookeeper is part of some vendor distributions. It's part of the Cloudera distribution, and we're going to be taking a look at it in just a couple of minutes. Why would you use Zookeeper? The most common use case is for distributed in-memory computation. What kind of business scenarios support distributed in-memory computation? Well, one of them would be ad serving. So you'd want to capture behavioral information, say about what someone was doing in an online game, and then you'd want to serve up ads based on what they're playing in the game. So how does it work? There's some data that's shared between the client nodes, and you really care about data synchronization. If people are playing the game and they're in a certain room and there's a certain type of item in the room, you want to show them that ad for that item when you see that their mouse moves on it, not 5 minutes later. That's not going to be relevant. So data synchronization matters. Now, there are a number of utility objects in Zookeeper, locking, synchronization, queues, and other types of objects that help you to set this data synchronization up more easily. As with some of the other libraries we've talked about in this section, setting up Zookeeper and getting it to work properly is pretty complex. You have to configure it correctly, and you've heard me say this a couple of times, but it's just as important here. It needs to be tested with production-level workloads. A common situation I see in working with new enterprise Hadoop customers is they test with just too small of an amount of data, they push to production, and then they haven't either configured or optimized correctly, and they get into trouble. So hopefully you'll avoid that. As with some of these libraries that I've talked about in this section, they look a little rough around the edges, and that's because, remember, the Hadoop ecosystem is pretty new. So there's a whole group of vendors out there that are providing alternatives that you have to buy that have a higher level of sophistication. So in general, but particularly with Zookeeper, what I often see is enterprises will start with Zookeeper because it's free and it's included as part of the Hadoop distribution for most vendors automatically. And they'll try it out and kind of see how it works. And then either they'll go with it or they will purchase a third-party product. So ones that I'm familiar with are Open Replica and something called Doozer. The names crack me up. We are once again in the Cloudera Hadoop virtual machine in the Hue browser. In earlier movies, we took a look at the options that are available on the various buttons here. Do you remember where Zookeeper was? Probably not, because we've gone over so many things. It's under the data browsers, which isn't the most intuitive place. But if you think about it, Zookeeper is designed for high-level coordination between clusters. And what do clusters contain? They contain data. So it does kind of make sense. Now, I'm going to click on Zookeeper, and it's not very exciting inside of here. Even though Zookeeper is installed, remember that this virtual machine is configured in what's called pseudo-distributed mode. Do you remember the difference between distributed and pseudo-distributed mode in a Hadoop cluster? Pseudo-distributed does not have any separate data nodes. Everything is running on a single machine. So the Zookeeper doesn't have a very big zoo here. It's just a single machine. Normally, you would use Zookeeper with a fully distributed Hadoop cluster, which would have hundreds, thousands, even tens of thousands of nodes. So you can see there's not going to be too much in the Z node hierarchy. We don't have anything other than the leader node here. So, but you could see if you were connected to clients, you could visualize this. So the first step in working with Zookeeper would be to set up a multi-node cluster. And how you would do that in this particular case is you would want to have multiple virtual machines and you would want to connect them. And you're able to do this with the Cloudera Developer Edition, and they do have instructions on how to do it. That's one way you could do it. Another way that I've worked with Zookeeper is to use a cloud-based setup, as I showed in an earlier movie with Amazon or with Microsoft, where it's really easy just to set up multiple nodes by setting that parameter configuration when you're spinning up the cluster. Well, we're on our last library that I'm going to talk about, believe it or not. Here we are, Spark. This is the kind of the newest, latest, greatest library as of the time of this recording. So what is Spark? Well, it's in-memory distributed data analysis. And you might say, hey, wait a minute, didn't we just see that with Impala? Well, we kind of did, but you may or may not remember, so I'll remind you that Impala is specific to one vendor's distribution. It's very interesting, the way that the Hadoop ecosystem is evolving. It's kind of evolving in parallel. You have these vendors that are making money by adding value onto core open source Hadoop distributions, by adding tools, by adding management, and possibly by adding libraries. So the example of Cloudera and Impala is one of the first examples of a vendor adding a piece of functionality that previously would have been coming out of the open source world. As you might have guessed, the open source world reacted by making their own library. So there is some discussion now whether Spark is the way going forward if you're on a Cloudera distribution, or whether Cloudera Impala is. You might remember from the Impala discussion that other vendors, such as Hortonworks, have worked to create their own version of in-memory Hive. So this is probably the most active area of the Hadoop ecosystem, as you might expect, because who doesn't want faster queries? So you've got all these competing libraries. And I know I've said this a couple times throughout this course, but this is very, very important around how you choose to implement your in-memory, if you do, implementation of querying. So Spark, in-memory distributed data analysis. The goal is to speed up a job or jobs. And what kind of jobs? Batches, machine learning jobs. Again, this goes along with the increasing sophistication and computational intensity, and interactive queries. So the need for speed. This is driving big data implementations, speed and complexity. Now, Spark is included with some distributions. Interestingly, it's included with the Cloudera distribution. So you've got kind of two competing things going on, and you can try both of them out. You've got Impala and you've got Spark. Now, one subtle difference between Impala and Spark is Impala is organized as a column store in memory, which is more of an analytic workload, a select or an aggregate type of thing, whereas Spark does not have that. Spark is an in-memory optimizer, so it's designed to optimize all Hadoop workloads, or the great majority of them. So the implementation, and I'll show you it briefly, in the Cloudera Hue editor is to upload and configure jar files. So to take jar files and then to pull them in to Spark so that they can be optimized for in-memory execution. Because we've covered so many libraries, again, I want to just quickly compare them. I myself get confused between Storm and Spark, so I thought I'd make this summary slide. Storm is very specialized. It's complex event processing, so the data streaming from sensors, per se. Impala is in-memory column store, so analytic-style queries, select, aggregate, grouping, and this is specific to Cloudera. Spark is in-memory Hadoop. It is also Yarn ready, which is MapReduce 2.0, and it is a way to implement Hive in memory as well. Now I'm actually going to show you the Spark implementation, which is pretty light. This is pretty new in this virtual machine. So in the query editor here, I'm going to go down to Spark, and you can see that I have editor, applications, dashboard, contexts, and uploads. All that I do here is I upload an app, and it's going to be basically a jar file. One class of the jar should implement a Spark job. So it's really just kind of a light wrapper, and there's no samples or anything inside of here. And then you would run this. I think it's interesting. It's called the Spark Igniter. And then you would see the information here about the execution. So it's really just a very lightweight framework. Also, you might notice you've got a link here where you can look at the Spark implementation. And you can see this is the Spark master, where you can also look at the overhead in memory, and it's all in memory, of your applications that are running. If you're going to use Spark, you can look both here or back in the Cloudera implementation over here. I'm going to add an update to this Apache Spark section because the landscape has matured since I first recorded this course. And what I'm finding in my work in cloud Hadoop architecture is that Spark is really dominating for my customers. It's not only in memory, which makes it tremendously fast. The Spark Databricks ecosystem is extremely well funded. I think they're on their Series E at the time of this recording. So they have a massive developer group along with the open source Spark committers. really, Spark has just dominated, and the Spark set of libraries have been increased to support almost all workloads that my customers need. So when I'm going to work with Hadoop these days, I'm going to start with Spark as my go-to set of libraries. In particular, there's a set of services that are really interesting around machine learning. It's called MLflow, which has been released relatively recently. I'm really seeing Cloudera fading in terms of innovation, although they still have their in-memory library, Impala. I really haven't found use cases for my customers, and it could be because my customers are cloud-based. I see Cloudera on-prem installations. Hortonworks has, of course, been acquired by Cloudera, and other vendors actually have gone out of business. So the ecosystem is really consolidating, and I'm seeing the growth around the Spark set of libraries, really more than any other set. In fact, there are other courses in the LinkedIn Learning Library that I encourage you to pursue. In this section coming up, we'll be taking a look at running Spark and Spark jobs on our trial cluster, and it'll get you started. But I think this is really the growth area, and I encourage you to continue your learning in this area with this course and others that are available. Here we'll work with Spark on our cluster. To start, I have some exercise files in my GitHub repo under Use Spark. And the first thing that we're going to do is we're going to run a jar file that's actually included on Google's distribution to calculate the digits of pi. And before we run that, let's actually look at the source code. So you can see here in the source code example, which comes from the Apache Foundation and is included in the Google distribution, lines 1 through 6 perform our imports. Now, if you were going to change this, you would need an IDE, probably with Eclipse, and you would need to import the binaries for Spark so that you could then build this into your own jar file. Like I said, the built jar file is included in the distribution we're working with. So I'm just showing this so you can see what the code is doing behind the scenes. I'm going to scroll down just a little bit. Our class is defined on line 8, and our entry point or main method is on line 10. You can see lines 11 through 14 work with the Spark session. In line 16, we're using a Java Spark context. We're using Java here. And in working with Spark, you can use a number of OOP languages. I did some production work with Scala, which is more of a functional language than Java. And it really comes down to personal preference, team expertise, and what kind of performance you're looking for. In lines 18 through 24, we're performing the work of the method. So we've got the definition of slices, where we're parsing, and we're setting this to the value in 19, so 100,000. In 20, we're defining a list of integers and setting that equal to a new array list. In 20 and 21, we're iterating over using a for loop and incrementing. In line 25, we're using the RDD, which is the primitive in Spark, the Java RDD, and we're setting that equal to our data set. Importantly, in 25, we're calling to our Java Spark context the parallelize method, so we're running this in parallel. In lines 27 through 31, we're performing the work to do the calculation for the digits of pi. So we're setting the count variable equal to a map of the data set in line 27. And then we're performing some math functions. And in line 33, we're outputting, and 35, we're ending our session. So what does this look like in Dataproc? As with some of the other videos, I've already run this previously, so you can see it took 42 seconds on our cluster. But just to show you what this looks like, you would submit the job, and you'd call it calc pi, and then you would select Spark. And like I said, on the distribution, I was looking around and I found that there's a Spark samples jar file. So you would put the main class, which is calculate pi, the arguments, which is, I think I ran it with 1,000, and then the path to the jar file. And then you would click submit. So looking at the job configuration of the successful run of this, the main class or jar file is Spark Pi, and this is case sensitive. And here is the path as of this recording on Google's image here. And if you do get an error on this, just SSH into the head node and verify the path of this particular jar file, Spark-examples. Sometimes also I've seen they put version numbers, so you want to look for this jar file if you have a problem running this job. And the output that you're expecting here is the digits of pi, so you can see pi is roughly 3.14. Also, I'll remind you that when you're working with Spark jobs, you have in your cluster, if you've chosen to install it, as we did, under the web interfaces, you have a Spark history server. So I've spun this cluster up and down, so I don't think I have anything in this history server because I didn't run any Spark jobs on this iteration, but I'll take a look here. Yeah, I didn't run anything here. So if I were to run this job, I could look in the history server and I could examine the output related to working with this job. As we're using different libraries to run jobs and scripts on our cluster, we have been working with this job interface. But because we installed some other utilities, we can use other methods of running jobs. And we're going to take a look now at using the web interfaces. In particular, we installed Jupyter when we set up this cluster. So I'm going to go ahead and open up Jupyter. And I previously uploaded, using the upload capability, a couple of IPython notebooks. And again, these notebooks are available in my GitHub. So you can just download it from the GitHub and then upload it here if you want to. So I'm going to open up word count. And in this case, we're working with Spark, but we're doing it with a scripting interface, which is Python for Spark or PySpark. So we've seen word count several times, and this is by design because it is the hello world or one of the hello worlds of working with Hadoop and Spark. And I think it's really useful to look at what it would entail to write it in the different libraries that you have available and what the performance overhead is. So it's interesting to see, if I go ahead and say view line numbers, that kind of impressively, we only need 4 lines here. So what are these lines? You can see in line 1, we're setting the file variable equal to our source data for word count. And as we've done in previous movies, we're using the data lake metaphor. So we're not interacting with the Hadoop file system because we're up on the cloud. We're using instead a cloud storage bucket. And so you can see it's GS, Hadoop course, Shakespeare raw. And if I go over here to my bucket, you can see here is my Shakespeare, and I've set this to public just for ease of demonstration by editing the permissions and setting all users to read. In line 2, we set the words to the Spark context, which is SC, which we get automatically as this client to our cluster. Text file passing in the file. Then we flat map this. That's a PySpark method using a lambda. And then we split the lines on spaces. We set the word counts variable equal to our variable words, calling the map method, again using a lambda, passing in word and 1. And then we call the reduce by key, and we increment. You can see the plus B at the end. Then at the end, we save as text file, and we save this into output. Now, I'll remind you that we have immutability in our writing, so we'd have to get a different location if we wanted to run this more than once. So we could verify just quickly by looking in our bucket to see if we had output already. So let's actually just look at the Hadoop course because it would fail if we had that. And we have output text, but we don't have output. So now if I go ahead and click in here and we run this, the star means that it's executing. And then when it turns to a number, it means it has completed. And there it's completed. And so if we go over here and we refresh, we can see we have an output folder, and inside of here we have our success message, and then we have our word count results, and so we're just going to download this. And you can see here is our word count. So again, using a cloud native method, it's been really interesting to interact with our cluster using Jupyter notebooks, which are commonly used in data science scenarios, and to use these modern libraries, in this case for Spark, PySpark. Again, if you want to get this notebook, it's over here. You just would download it from my GitHub source files. In my consulting practice, I'm working with customers often on Hadoop Spark clusters that computationally are going to run machine learning workloads. And it's interesting because both Hadoop Spark and machine learning ecosystems are evolving. Just a few years ago, many of the machine learning that was implemented was scikit-learn, k-means, logistic regression, and that's still around. And even some of the native Hadoop libraries like Mahout. What I'm seeing now more frequently, though, is demand for more innovative and modern machine learning libraries, principally TensorFlow, and that can often add demand for GPUs. And you see that in the GCP implementation on Dataproc, that you can add GPUs so that you can work with distributed neural networks or convolutional neural networks. Spark itself has been adding a series of services, most notably MLflow, as of this recording, to make the productization of machine learning workloads smoother. So, it is a really fast-moving ecosystem, and if you have a project that has these requirements, you really want to look at what's going on in the Spark world, look at what Databricks is doing, and you want to look at what Google's doing in the machine learning world as kind of a leading edge. So why is this the case that machine learning runs on Hadoop clusters? It has to do with the data volume. I mean, Hadoop by its nature is distributed and so can handle massive amounts of data. Also, there's often computational complexity. These are often sparse matrix calculations that can be computationally huge and complex. Often, there's iteration involved in this because machine learning is often used for problems for which the answers are not known. Sometimes the questions aren't even known when we have unsupervised machine learning. Often Spark is added to these clusters because of speed, so it can have in-memory processing. And personally, I've been working really pretty solidly in the area of genomics in this implementation of Hadoop and machine learning. So here's an example of implementing custom machine learning on Spark from genomics, some work that I had done with CSIRO and bioinformatics in Australia. I've written about this on Medium, so you can see the source code by searching on my name if you want to know more about this. This architecture is built on Amazon. So this is EMR, so it's similar conceptually to GCP Dataproc. It's a managed cluster, and we moved it from on-prem to cloud and got a very substantial performance improvement, which they were looking for. It went from 500 hours per run on-prem to a few hours, and they had a shared on-prem cluster, so they couldn't submit and get answers to their questions. They had to wait in a queue, basically. And by leveraging cloud, they were able to get their own cluster and be able to iterate on their research. So it really did provide great value for them. So as we've seen in this course, increasingly, Hadoop Spark workloads run on public cloud data lakes rather than HDFS. And this is a substantial change to working with Hadoop that I've encountered in the past few years. Basically, all of my clients in the past 12 to 18 months are now moving towards public cloud data lakes because they're more scalable, they can be less expensive, and is really just a shift I'm seeing in the Hadoop industry. So the Hadoop cluster file systems, I'm really seeing NTFS or other file systems such as DFS fade. DFS would be used, of course, that's the Databricks file system, if you're using Databricks on-prem. And other Hadoop proprietary file systems, some of those companies are no longer in existence, such as MapR, for example. So I'm seeing that data lakes are cheap, they're flexible. Other services on the cloud can use them. So, for example, if you're using an Amazon data lake, you could use Athena SQL processing on top of that data lake in addition to EMR. There's less data movement because they just basically put your data up in the object store and then select your compute to run on top of it. And I'm really seeing Amazon S3 and GCP, Google Cloud Storage, lead in this way. As of this recording, Amazon has announced a service called Amazon Data Lake to help you to manage massive amounts of data in their object store. Now, to continue the example that I showed in a previous movie, the second iteration of this particular example, we did build on a data lake. So we're still using Hadoop Spark for the compute. In this case, we actually used customized Docker containers, and we got some really good economies of scale. We went from a couple of hours down to 10 minutes for the job run. So it was pretty significant. And because we wanted to be open in terms of running on multiple clouds, we used the Terraform configuration scripts rather than CloudFormation. And we used Docker technologies so that although we initially set up on Amazon, we could run on Google or Azure or anything else because we're using Docker images. It was interesting that during this project, Hadoop Spark was extended so that Kubernetes could be used as a scheduler in place of Yarn. So this is relatively recent. And of course, with this, we were then able to disrupt and no longer use HDFS and use S3 in this case in a true data lake as our file system. So again, I wrote on this work on Medium, and I have all the source code available on GitHub. So if you want to take this as an exercise to take a look at it or even build part of it, we wanted to build it as a reference implementation in addition to solving this customer's need. The complexity of distributed data systems is non-trivial. And as with many complex technical situations, I think visualization is really important. Visualization at every aspect of working with Hadoop has been a reason I've been successful with customers. In particular, the visualization of the work running on the cluster has really helped me in performance tuning and getting great value. To that end, visualization libraries that I've worked with are Ganglia, which has a number of visualizers around cluster performance and is available to be included with AWS EMR. There are also a number of powerful third-party and other public cloud visualization tools, such as GCP Stackdriver. In addition to that, the data that's output from the results of running Hadoop Spark jobs can be pretty darn complex. In addition to using traditional visualization tools such as Tableau or custom clients, D3, I've had some really good success in working with researchers using visualization libraries that are available and used in Jupyter notebooks. These include R libraries, Python libraries, and others. And just to give you a picture of what Amazon EMR and Ganglia can look like, as I had been referencing the data lake for custom machine learning that my team and I helped the CSIRO bioinformatics research team in Australia move to the cloud, we did use Ganglia extensively when we were figuring out the most optimal hyperparameter settings for the cluster, the machine learning algorithm, and the solution in general. And it really helped us get to market faster. Well, we've come to the end of our tour of the Hadoop ecosystem. As you've learned, it's a rich and varied ecosystem, and most people who work with it are going to want to continue learning. So I have a couple tips for that end. First, you want to use or expand your development environment, and that might include also spinning up some Hadoop clusters in the cloud. Second, I suggest that you focus on a subset of Hadoop skills. And the two areas of focus usually are either developer or analyst, so you'll learn more about writing and optimizing queries, or administration, and there you'll learn more about monitoring and security. Thanks for listening.